So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, there are particles of light hitting your skin. Trillions of them every single second, washing over you like invisible rain. Some of those particles left the lamp on your bedside table a billionth of a second ago. Others left a star so far away that they've been traveling since before the dinosaurs went extinct. And here's what's really strange. For 300 years, some of the smartest people who have ever lived fought a war over what those particles actually are. Not a polite disagreement. A genuine, bitter, careers-on-the-line scientific war. On one side, a camp that said light is made of tiny bullets, little hard grains of energy that fly in straight lines and bounce off mirrors like billiard balls. On the other side, a camp that said light is a wave, a ripple spreading outward the way sound spreads through air or waves spread across a pond. Both sides had evidence. Both sides had brilliant champions. And for 3 centuries, the pendulum swung back and forth between them. Particle, wave, particle again, wave again. Each swing more dramatic and more confusing than the last. And then, in the 20th century, something happened that nobody expected. The pendulum broke, because the universe turned out to be stranger than either side had imagined. Light, it turned out, isn't a particle, and it isn't a wave, and yet, somehow, impossibly, it's both at the same time. Or maybe neither, depending on how you ask the question, depending, it seems, on whether you're even looking. So tonight, we're going to walk through the whole story of how humans tried to answer one seemingly simple question. What is light? We'll start at the very beginning and move slowly through 25 centuries of wrong answers, brilliant guesses, bitter feuds, and experiments that shattered everything. And along the way, there are a few questions I want you to hold in your mind as we go. When a photon from a distant star arrives at your eye, what did that photon experience during its journey across the universe? The answer is nothing. Not a single instant of time. For the photon, the moment it left that star and the moment it hit your retina were the same moment. How is that possible? And here's another one. When physicists fire a single photon at a wall with 2 slits in it, that photon, a single particle, somehow goes through both slits at the same time and interferes with itself. Unless you watch it. If you put a detector at the slits to see which one it goes through, it stops doing that. It picks one slit and behaves normally. Light changes its behavior depending on whether anyone is looking. Why? And maybe the biggest question of all, after everything we've learned, after 3 centuries of the most intense scientific investigation in history, do we actually know what light is? Or have we just gotten very good at describing what it does? That's what we're going to walk through tonight. Slowly, carefully, from the very beginning. The whole story of light, from the first people who wondered about it to the experiments that shattered everything we thought we knew. And along the way, you'll meet some of the most brilliant, stubborn, eccentric human beings who ever lived. People who staked their entire reputations on getting this one question right. If you drift off somewhere along the way, that's perfectly fine. The story will still be here. And honestly, some of these ideas settle in more naturally when your mind is loose and half asleep, not trying too hard to force everything into boxes. Because that's sort of the lesson of this whole story. Light refuses to be put in a box. Every time someone tried, it found a way out. Let's start where most big questions in science start. Let's start with people just looking at the world and wondering. For most of human history, light was simply there. It was the sun in the morning and the fire at night and the stars overhead, and nobody spent much time asking what it actually was, because what would you even compare it to? Light was light. It let you see things. That was enough. But eventually, as with most things, the Greeks started asking questions. Around the 5th century BC, a group of thinkers in the Greek world began to wonder about the mechanics of vision. And they came up with an idea that sounds bizarre to us now, but made a kind of intuitive sense at the time. They proposed that seeing worked because your eyes sent out invisible rays, like tiny feelers or tentacles of perception, that reached out and touched the objects around you. You saw a tree because your eye beams touched the tree. You saw a mountain because your eye beams reached all the way to the mountain. This was called the emission theory of vision, and it was supported by some genuinely serious thinkers. Euclid, the father of geometry, wrote an entire treatise on optics based on this idea. Ptolemy, the great astronomer, also worked within this framework. And if you think about it, you can see why the idea was appealing. Your eyes do seem to actively reach out into the world. You choose what to look at, you direct your gaze. It feels, subjectively, like your eyes are doing something, projecting outward, scanning, searching. The feeling of looking at something is an active feeling, not a passive one. But there was an obvious problem, and some Greeks noticed it. If your eyes send out rays that let you see, then why can't you see in the dark? If vision is something your eyes do, it shouldn't matter whether the room is lit or not. Your eye beams should work just as well at midnight as at noon. And yet, clearly, they don't. You need light to see. External light, the sun, a torch, a candle. Something out there has to be doing something for your eyes to work. This observation pushed some thinkers toward a different model. Maybe, they suggested, objects themselves send out something, some kind of influence or emanation, and your eyes receive it. Light doesn't come from your eyes. Light comes to your eyes. Aristotle leaned in this direction. He thought of light as a kind of activity in a transparent medium, not a thing that travels, but a state that a medium can be in. When a medium is activated by a luminous source, it becomes transparent and you can see through it. When the source goes away, the medium goes dark. These ideas were creative, but they were also, by modern standards, pretty vague. Nobody could say precisely what light was made of, or how it traveled, or how fast it went, or whether it even traveled at all. For the ancient Greeks, light remained more of a philosophical puzzle than a scientific one. They asked the right questions, which is no small thing, but the tools and techniques needed to answer those questions wouldn't exist for another 2,000 years. And for most of those 2,000 years, the question of what light actually is sat mostly dormant in the Western world. The Roman Empire rose and fell. The Middle Ages came and went. Scholars in medieval Europe mostly accepted Aristotle's framework without pushing much further. But across the Mediterranean, in the Islamic world, something important was happening. In the 10th and 11th centuries, a succession of brilliant scholars was doing something that would change the way humans think about light forever. And the most important of them was a man named Ibn al-Haytham. Ibn al-Haytham was born in Basra, in what is now Iraq, around the year 965. He was, by any measure, one of the greatest scientists of the medieval world, and his contributions to optics were so foundational that he's sometimes called the father of modern optics, which is not an exaggeration. Here's what made Ibn al-Haytham different from the Greek philosophers who came before him. He didn't just sit and think about light, he did experiments. He built dark rooms with small holes in the walls and watched how light from the outside world projected an inverted image on the opposite wall. He studied how light reflects from mirrors, how it bends when it passes through water or glass. And most importantly for our story, he firmly and decisively settled the question of whether light comes from the eyes or from external sources. Light, Ibn al-Haytham declared, enters the eye from outside. We see because light from the sun or from a flame bounces off objects and travels in straight lines into our eyes. Vision is a passive reception, not an active projection. The eye is a receiver, not a transmitter. This might seem obvious to us, but remember, the emission theory, the idea that eyes send out rays, had been the dominant view for over 1,000 years. Ibn al-Haytham dismantled it through careful reasoning and systematic experimentation. He noticed, for example, that looking directly at the sun hurts your eyes. If your eyes were the ones sending out the rays, why would receiving light from the sun cause pain? Clearly, something from outside is entering the eye, and when that something is too intense, it causes damage. The logic was clean, and the experiments were persuasive. Ibn al-Haytham's Book of Optics, written around 1011 to 1021, was translated into Latin and became enormously influential in Europe during the Renaissance. Centuries of European optical science built directly on his work. And yet, even with all of Ibn al-Haytham's contributions, one enormous question remained completely unanswered. We knew that light travels. We knew it comes from outside. We knew it bounces off objects and enters our eyes. But we still had no idea what it actually is. Is it a substance? A fluid? A stream of particles? A vibration in some invisible medium? Nobody knew. And nobody would seriously crack the question until the 17th century, when two titans of science took up opposing positions and set the stage for a war that would last 300 years. But here's the thing. Before we can understand that war, we need to meet the man who fired the first shot. And to do that, we need to travel to England in the 1660s, to a quiet room in Cambridge, where a young, solitary, and extraordinarily intense man was playing with a piece of glass and a beam of sunlight. His name was Isaac Newton, and what he was about to discover would make him famous, make him enemies, and set the terms of a debate that physics still hasn't fully resolved. So let's talk about Newton and his prism, because it's one of the most famous experiments in the history of science, and it's also one of the most misunderstood. Most people know the basic story. Newton took a glass prism, held it up to a beam of sunlight coming through a hole in his window shutters, and watched as the white light fanned out into a rainbow of colors on the far wall. Red, orange, yellow, green, blue, violet. The spectrum. Every physics textbook has the picture. But the real significance of what Newton did goes much deeper than just making a pretty rainbow. Before Newton, the prevailing view was that white light was pure, fundamental, and simple. Colors were thought to be modifications of white light, corruptions of it, created by the glass or the medium that the light passed through. The prism, people assumed, was doing something to the light, staining it, coloring it, altering it in some way. White goes in, colors come out, and the colors are the prism's doing. Newton proved that this was wrong. And the way he proved it was beautifully clever. After splitting white light into a spectrum with his first prism, he took a second prism and placed it in the path of just one color, say, the red portion of the spectrum. If the first prism was creating the colors, then the second prism should modify the red light further, perhaps turning it some other color. But it didn't. The red light passed through the second prism and came out still red. It was bent, refracted, yes, but its color didn't change. Then Newton did something even more decisive. He took all the colors that the first prism had spread out and recombined them using a second prism, and they merged back into white light. The prism wasn't creating colors, it was separating them. White light, Newton showed, is not simple. It's a mixture, a composite of all the colors of the rainbow blended together. The prism just pulls them apart because each color bends by a slightly different amount as it passes through the glass. This was a genuine revelation. White light is not fundamental, it's compound. The colors are what's fundamental, and white is what you get when you mix them all together. Newton published these findings in 1672 in a paper sent to the Royal Society in London, and the reaction was explosive. Some people were thrilled, others were outraged, and one person in particular was furious. His name was Robert Hooke. Now, Hooke and Newton are one of the great rivalries in the history of science, and their feud over light is where much of the venom originated. Hooke was already an established figure at the Royal Society when Newton's paper arrived. He was the Society's curator of experiments, a brilliant polymath who had published his own major work on optics, a book called Micrographia, back in 1665. And Hooke had his own views about the nature of light, views that clashed directly with what Newton was proposing. See, Newton didn't just describe his prism experiments, he also proposed a theory about what light actually is. And his theory was that light consists of tiny particles, what he called corpuscles. Little grains of luminous matter, flying through space in straight lines at enormous speed. Different colors, Newton suggested, correspond to corpuscles of different sizes. The prism separates them because the glass bends corpuscles of different sizes by different amounts, the way a sieve sorts grains of different diameters. Hooke disagreed, vehemently. Hooke believed that light was a vibration, a pulse, a wave propagating through some medium. He had said as much in Micrographia, and he wasn't about to let this young Cambridge upstart overturn his position. He wrote a dismissive critique of Newton's paper, suggesting that Newton's experiments were fine, but his theoretical interpretation was misguided. Newton was livid. He took criticism personally, always, and Hooke's review wounded him deeply. Newton wrote furious replies. The correspondence grew heated, and the bitterness between the two men would simmer and occasionally boil over for decades. It's worth noting that there are no surviving portraits of Robert Hooke. For years, a rumor persisted that Newton himself was responsible for the disappearance of Hooke's likeness, having conveniently lost it when he took over as president of the Royal Society after Hooke's death in 1703. Newton has since been cleared of any deliberate wrongdoing, but the fact that the rumor existed at all tells you something about how deep the animosity ran. But Newton's dispute with Hooke wasn't just personal, it was scientific, and it touched on a question that would consume physics for the next 3 centuries. Is light a particle or a wave? Newton's particle theory, his corpuscular theory, had real strengths. It explained beautifully why light travels in straight lines. Particles travel in straight lines unless something deflects them. It explained reflection neatly. Corpuscles bounce off a mirror the way a ball bounces off a wall. It could account for refraction, the bending of light as it passes from one medium to another, by supposing that the particles speed up when they enter a denser medium like glass or water, pulled in by some attractive force at the surface. And Newton's theory made a bold prediction that went beyond anything his contemporaries had considered. He suggested that light, being made of particles with mass and momentum, should be affected by gravity. Light, Newton wrote in his book Optics, published in 1704, should bend when it passes near a massive object. Do not bodies act upon light at a distance, and by their action bend its rays? That was a stunning prediction, and it would take more than 2 centuries before anyone could test it. When they finally did, Newton turned out to be right, though the mechanism was completely different from what he'd imagined. But we'll get to that later. The particle theory also had a crucial advantage that had nothing to do with physics. It had Newton. And in the early 18th century, having Newton on your side was like having gravity on your side. His reputation was so immense, his authority so overwhelming, that his corpuscular theory dominated the scientific landscape for the better part of a century, not necessarily because the evidence was conclusive, but because arguing with Isaac Newton was something most people preferred not to do. But here's the thing about Newton's particle theory. It couldn't explain everything, and the things it couldn't explain would eventually prove to be its undoing. There was, for example, a phenomenon called diffraction. When light passes through a very narrow opening or past a sharp edge, it doesn't just continue in a straight line. It spreads out slightly. It bends around corners just a little. Now, if light is made of tiny bullets, Why would those bullets curve around an obstacle? Bullets don't do that. They fly straight. Sound, on the other hand, does bend around corners. You can hear someone talking from around the side of a building, even though you can't see them. And sound is a wave. Waves bend around obstacles. Particles don't. There was also a phenomenon called Newton's rings, which Newton himself had actually discovered and studied extensively. When you press a curved glass lens against a flat glass plate, you see a pattern of concentric colored rings at the point of contact. Newton spent years studying these rings, measuring them with extraordinary precision, and the pattern they formed was, honestly, much easier to explain if light was a wave than if it was a particle. The rings look exactly like an interference pattern, the kind of pattern you get when two waves overlap and either reinforce or cancel each other. Newton knew this. He wasn't blind to the difficulties. In his private notes, he wrestled with these problems, sometimes flirting with wave-like ideas, sometimes retreating to his particle model. But in his published works, he came down firmly on the side of corpuscles, and his authority carried the day. Meanwhile, across the English Channel, a Dutch scientist was developing a very different picture of light. And his ideas, though largely ignored during his lifetime, would eventually come roaring back. Christian Huygens was born in The Hague in 1629. His father was a prominent diplomat and man of letters who counted René Descartes among his friends. Young Christian grew up surrounded by intellectual stimulation and showed a talent for mathematics and physics from an early age. He went on to become one of the most accomplished scientists of the 17th century, inventing the pendulum clock, discovering the largest moon of Saturn, and making fundamental contributions to mechanics, astronomy, and optics. And on the question of light, Huygens stood squarely opposed to Newton. Huygens believed that light was a wave. Not a wave of water or air, but a wave in some invisible, all-pervasive medium that filled the universe, a medium he called the ether. Just as sound needs air to travel through, light, Huygens argued, needs the ether. And when a luminous source like a candle or a star produces light, it creates disturbances in the ether that ripple outward in every direction, like the expanding circles you see when you drop a stone into a still pond. In 1690, Huygens published a book called Treatise on Light, in which he laid out his wave theory in detail. He showed how his model could explain reflection and refraction just as well as Newton's particle theory, and in some cases better. His explanation of refraction in particular was elegant. Where Newton's particle theory required light to speed up when entering a denser medium like glass, Huygens's wave theory predicted the opposite, that light would slow down in glass. This was a crucial difference, and it would eventually be testable. But in the 17th century, nobody had the equipment to measure the speed of light inside glass, so the point remained unresolved. Huygens also developed a powerful mathematical tool for understanding wave propagation, now called Huygens's principle. The idea is that every point on a wavefront can be thought of as a source of new wavelets, tiny circular waves radiating outward. The new wavefront at any later moment is the envelope of all those wavelets. It's a beautiful construction, and it allowed Huygens to derive the laws of reflection and refraction from first principles, purely as consequences of wave behavior. But despite the elegance of Huygens's theory, it struggled to gain traction during his lifetime. Newton's reputation was simply too powerful, and there was a genuine weakness in the wave theory that Newton and his supporters were quick to point out. If light is a wave, why does it travel in straight lines? Waves, after all, spread out. Sound goes around corners. Water waves expand in all directions. But light casts sharp shadows. It travels in straight lines so precisely that you can use it to survey land or aim a telescope. How can a wave do that? The answer, which wouldn't become fully clear for another century, is that it depends on the wavelength. Waves bend around obstacles that are comparable in size to their wavelength. Sound waves have wavelengths measured in feet or meters, so they easily bend around human-sized obstacles like walls and pillars. But if light is a wave with an extraordinarily tiny wavelength, much smaller than any everyday object, then it would travel in what appears to be a straight line under ordinary circumstances. It would only show its wave-like nature when forced through openings comparable to its tiny wavelength, which is exactly what happens in diffraction. But in the late 1600s and early 1700s, nobody knew this. The wavelength of light hadn't been measured, and so Newton's objection seemed powerful, and his corpuscular theory held the field. And this is where things stood for about 100 years. Newton's particle theory reigned supreme, more because of Newton's authority than because of decisive experimental evidence. Huygens's wave theory lingered in the background, respected by some, but largely overshadowed. The pendulum, in our metaphor, was stuck all the way over on the particle side. And then, around the turn of the 19th century, the pendulum began to swing. The person who pushed it was a young English physician and polymath who might be the most underrated genius in the history of science. His name was Thomas Young, and what he did in a darkened room in London around the year 1801 would change everything. Thomas Young was born in 1773 in the tiny Somerset town of Milverton. He was, by any reasonable standard, a prodigy. He could reportedly read fluently by the age of 2. By 14, he had learned Greek, Latin, French, Italian, Hebrew, Arabic, Persian, Turkish, and Ethiopian. He went on to study medicine and became a practicing physician, but his interests ranged far beyond medicine. He made major contributions to the theory of elasticity, helped decipher Egyptian hieroglyphics from the Rosetta Stone, and produced important work in physiology, linguistics, and music theory. But the thing Young is most famous for, the experiment that would turn the light debate on its head, involved a beam of light and 2 narrow slits. Here's what Young did. He took a source of light and directed it at a barrier with 2 very thin, parallel slits cut into it. On the other side of the barrier, he placed a screen. Now, if light is made of particles, as Newton said, you'd expect a simple result. Some particles would go through one slit, some through the other, and on the screen, you'd see 2 bright strips of light, one behind each slit. 2 slits, 2 bands of light. Straightforward. But that's not what Young saw. Instead of 2 bands, the screen showed a pattern of alternating bright and dark stripes. Multiple bands of light and darkness spread out across the screen in a regular repeating pattern. Young recognized this immediately for what it was. He had seen patterns like this before, in water. When 2 sets of ripples cross each other on a pond, they create exactly this kind of pattern. Where the crest of one wave meets the crest of another, the waves reinforce each other, building up a higher combined wave. That's called constructive interference, and it produces a bright band. Where the crest of one wave meets the trough of another, they cancel each other out. The water goes flat. That's destructive interference, and it produces a dark band. Young was seeing exactly the same thing with light. The light passing through the 2 slits was behaving just like 2 sets of water waves crossing each other. It was interfering with itself, and interference is something that only waves do. Particles don't interfere. If you threw tiny pebbles at a wall with 2 holes in it, the pebbles that made it through would just pile up in 2 heaps. They wouldn't create alternating bands of more pebbles and fewer pebbles. Young's double-slit experiment was, and still is, one of the most beautiful and consequential experiments in the history of physics. In a single stroke, it provided powerful evidence that light is a wave. And it did something else too. From the spacing of the bright and dark bands on his screen, Young was able to calculate the wavelength of light. The number he got was extraordinarily small, on the order of a millionth of a meter. That's why light appears to travel in straight lines under everyday conditions. Its wavelength is so tiny compared to the objects around us that it barely diffracts at all. Only when you force it through a slit, comparable to that tiny wavelength, does the wave nature reveal itself. Now you might think that Young's experiment would have been greeted with universal acclaim. Here was clean, decisive experimental evidence for the wave nature of light. Newton's particle theory couldn't explain the interference pattern. The wave theory could. Case closed, right? Not quite. When Young first presented his ideas to the Royal Society in 1800, the reception was hostile. Newton's reputation still loomed enormous over British science, and suggesting that Newton had been wrong about light was, in that cultural context, almost heretical. One reviewer in the Edinburgh Review wrote a scathing attack on Young, dismissing his wave theory as fanciful and his experiments as inconclusive. The tone of the review was so vicious that it effectively silenced Young on the topic for years. But Young was right. And slowly, over the following decades, other experiments confirmed and extended his findings. In France, Augustin-Jean Fresnel independently developed a comprehensive wave theory of light, complete with rigorous mathematics, that could explain not just interference and diffraction, but also polarization, a phenomenon where light waves vibrate in particular directions. Fresnel's work was meticulous and convincing, and by the 1820s and 1830s, the wave theory of light had effectively won. Newton's corpuscular theory was in full retreat. The pendulum had swung. Particle to wave. Newton's century-long dominance was over. Light, the scientific community agreed, was a wave. And here's a detail about Fresnel that I think is worth lingering on, because it shows the kind of person who pushes science forward. Augustin-Jean Fresnel was born in 1788 in Normandy, France. He was sickly as a child and didn't learn to read until he was 8 years old. His teachers didn't consider him particularly promising, but as a young man, he developed a passion for mathematics and physics, and by the early 1810s, he had begun working on optics entirely on his own, largely unaware of Thomas Young's earlier work in England. Fresnel was an engineer by training and by temperament. He didn't just theorize about light, he built things. He designed and tested optical instruments. He ground lenses. He set up experiments in his workshop and measured everything with painstaking precision. When he developed his wave theory of light, he backed it up not just with mathematics, but with detailed experimental data that left very little room for skepticism. One of his most important contributions was his explanation of polarization. Newton's particle theory struggled with this phenomenon. If light is made of particles flying in a straight line, why should those particles care about orientation? What does it mean for a bullet to be polarized? Young had also struggled with this, initially proposing that light waves vibrate back and forth along the direction of travel, like sound waves. But Fresnel showed that light waves vibrate perpendicular to the direction of travel, that they're transverse waves, not longitudinal. This was a crucial insight, because transverse waves can be polarized while longitudinal waves cannot. A rope shaken side to side can be oriented vertically or horizontally. A compression wave in air can't. And Fresnel's practical genius led to one of his most lasting contributions, the Fresnel lens. Traditional lenses are solid, heavy chunks of glass, and for lighthouses, the lenses needed to be enormous. Fresnel realized that you could achieve the same focusing effect with a fraction of the glass by cutting the lens into concentric rings and collapsing them into a flat profile. The Fresnel lens was lighter, thinner, and far more practical than a solid lens. Lighthouses around the world adopted Fresnel lenses, and they saved countless lives at sea. To this day, if you look at a lighthouse lens, you're looking at Fresnel's design. Fresnel died of tuberculosis in 1827 at the age of just 39. He received the Rumford Medal from the Royal Society of London shortly before his death, a recognition of his work on light from the very institution that had once sided so firmly with Newton's particle theory. When told of the honor, Fresnel reportedly said that he would have preferred a little more time. He didn't get it. but his wave theory outlived him by centuries. Now, there's another dimension to this story that we should spend some time with, because it connects the physics of light to something deeply personal. And that's the question of color. When Newton split white light into its spectrum, he identified 7 colors: red, orange, yellow, green, blue, indigo, and violet. The rainbow. But here's something that most people don't realize. The colors you see when you look at a rainbow are not a property of the light itself. They're a property of your brain. Light has a frequency. That's a physical fact, measurable with instruments, objective. Red light has a frequency of about 430 trillion oscillations per second. Blue light oscillates at about 680 trillion times per second. These are real, physical properties of the electromagnetic wave. But red and blue are not in the light. Red and blue are in your head. They're labels your brain assigns to different frequencies. The light itself has no color. It has a frequency, and your visual system, the cones in your retina and the processing circuitry in your visual cortex, translates that frequency into an experience, a subjective sensation that you call a color. This is why color blindness exists. The light arriving at a colorblind person's eyes is identical to the light arriving at anyone else's eyes. The frequencies are the same. But the cones in the retina respond differently, and the brain's interpretation is different, and so the experience of color is different. The physics is the same, the perception is not. And this goes deeper than color blindness. There's no way to know whether your experience of red is the same as mine. We both call it red. We both point at the same tomato and agree it's red. But whether the subjective experience in your mind is the same as the subjective experience in mine is a question that no experiment can answer. Philosophers call this the problem of qualia, and it remains one of the hardest problems in the philosophy of mind. What we can say is that the electromagnetic spectrum is continuous. There are no sharp boundaries between colors. The rainbow fades smoothly from red to violet, with no dividing lines. The boundaries between red and orange and yellow are conventions, imposed by human perception and human language, not by physics. Other animals perceive the spectrum differently. Bees can see ultraviolet light, which is invisible to humans. Many birds have 4 types of color receptors instead of our 3, giving them access to colors we literally cannot imagine. Mantis shrimp have 16 types of photoreceptors. The electromagnetic spectrum is the same for all of them, but the perceptual slicing is completely different. Newton chose 7 colors because he liked the analogy with the 7 notes of the musical scale. There's nothing physically special about 7. The spectrum is a continuum, and how many colors you see in it depends on the biology of your eyes and the language of your culture. And that brings up a remarkable intersection of physics and linguistics. Research has shown that cultures with more color words in their language are better at distinguishing colors. Speakers of Russian, which has separate basic words for light blue and dark blue, are measurably faster at distinguishing between those shades than speakers of English, which uses a single word modified by adjectives. The physics is the same, the frequencies are the same, but the perception changes with the language. Light, it seems, is not just a physical phenomenon, it's a perceptual one. And the boundary between what light is and what we make of it is not nearly as sharp as we might like to think. This connects to something about Maxwell's discovery that deserves emphasis. When Maxwell showed that visible light is just a tiny sliver of the electromagnetic spectrum, he revealed that the universe is full of light we cannot see. Infrared, ultraviolet, X-rays, gamma rays, radio waves, microwaves, all of it is the same thing as visible light, just at frequencies our eyes can't detect. The electromagnetic spectrum stretches from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than an atomic nucleus. Visible light occupies a narrow band in the middle, spanning less than 1 octave of the spectrum. less than 1 octave out of 60 or more. We are, in a very real sense, nearly blind. The universe is blazing with electromagnetic radiation that we can't see. Stars emit across the full spectrum. Galaxies glow in radio and X-ray and infrared. The cosmic microwave background fills every cubic centimeter of space, and we, with our puny 3-color vision, see almost none of it. All of our technology for seeing the invisible universe, radio telescopes, X-ray satellites, infrared cameras, microwave detectors, all of it is a way of extending our senses beyond the tiny window that evolution gave us. Every time we build a new kind of telescope, we open a new window onto the cosmos, and what we see through that window is always surprising. Radio telescopes revealed quasars and pulsars. X-ray telescopes showed us black holes devouring matter. Infrared telescopes pierced through the dust clouds that hide stellar nurseries. Microwave detectors gave us the cosmic microwave background, the oldest light in the universe. Each new window is a new chapter in the story of light. Each one confirms that light, across the entire spectrum, obeys the same physics, the same Maxwell's equations, the same quantum mechanics. A radio photon and a gamma-ray photon are the same kind of thing, differing only in frequency. And both exhibit the same wave-particle duality, the same quantum strangeness, the same refusal to fit neatly into human categories. The universe communicates with us through light. It's virtually the only messenger we have. Almost everything we know about the cosmos beyond our own planet, every star, every galaxy, every nebula, every quasar, we learned by catching photons and analyzing them. Light is the universe's way of telling us about itself. And the story it tells, once you learn to listen, is deeper and stranger and more beautiful than anyone imagined when the Greeks first asked what it was. But if light is a wave, one question remained glaringly unanswered. A question that had been nagging at people since Huygens first proposed his theory back in 1690. If light is a wave, what is it a wave of? What is doing the waving? Every other wave that people knew about was a disturbance in some physical medium. Sound is a wave in air. Ocean waves are waves in water. Seismic waves are waves in rock. A vibrating guitar string is a wave in the string itself. In every case, there's a substance that vibrates, a medium that carries the disturbance from one place to another. Take away the medium, and the wave disappears. Sound can't travel through a vacuum because there's no air to vibrate. So, if light is a wave, there must be a medium, some substance filling all of space, through which the light wave propagates. This hypothetical medium had a name. It was called the luminiferous ether, from the Latin word for light-bearing. And for most of the 19th century, physicists were absolutely convinced it existed. It had to exist, because without it, the wave theory of light made no sense. But what kind of substance would the ether have to be? Think about what we're asking it to do. It has to fill the entire universe, because light travels across the vast emptiness of space from distant stars to our eyes. It has to be perfectly transparent, because we can't see it or feel it. It has to be incredibly rigid, because light waves travel at enormous speed, and the speed of a wave depends on the stiffness of the medium. Sound in steel travels much faster than sound in air, because steel is much stiffer. For light to travel at 300,000 kilometers per second, the ether would have to be fantastically rigid, stiffer than the hardest diamond. And yet, this ultra-rigid, universe-filling substance would also have to offer absolutely no resistance to the motion of planets and stars, because the Earth swings around the Sun year after year with no sign of slowing down. An ether that is simultaneously infinitely rigid and perfectly permeable to matter is, well, a tall order. Physicists acknowledged these difficulties, but they pressed on. The ether had to exist. The alternative, a wave that waves through nothing, seemed like nonsense. And this is where one of the great geniuses of 19th century physics enters our story. A man whose work would not only explain what light is at a level nobody had achieved before, but would also, inadvertently, light the fuse that would eventually blow up the ether and everything that went with it. But before Maxwell entered the picture, someone else had already been thinking about this problem, not with equations, but with physical intuition. And his story is one of the most unlikely in the history of science. Michael Faraday was born in 1791 in Newington Butts, a poor neighborhood in South London. His father was a blacksmith who was frequently ill. The family had very little money, and young Michael's formal education ended at age 13 when he was apprenticed to a bookbinder. But Faraday read the books he was binding, and one of them, a popular science book called Conversations on Chemistry by Jane Marcet, captured his imagination completely. He began attending public lectures on science at the Royal Institution, and he took meticulous notes, eventually binding them into a book and sending them to Sir Humphrey Davy, the most famous chemist of the day. Davy was impressed enough to hire Faraday as his laboratory assistant. From that humble beginning, Faraday rose to become one of the most important experimental scientists who ever lived. And his contributions to our understanding of light are woven through the entire story we've been telling. It was Faraday who discovered electromagnetic induction, the principle that a changing magnetic field creates an electric current. This is the foundation of every electric generator and electric motor on the planet. Without Faraday's discovery, there would be no electrical grid, no power plants, no modern civilization as we know it. And it was Faraday who introduced the concept of the field. Before Faraday, physicists thought of forces as acting at a distance, a kind of instantaneous, invisible reach across empty space. Newton's gravity works this way. The sun pulls on the Earth across 93 million miles of vacuum, instantaneously, with no intermediary. Faraday found this deeply unsatisfying. He felt that there had to be something in the space between two magnets, something carrying the force from one to the other. He called it the field, the magnetic field, the electric field. Lines of force spreading outward from charges and magnets, filling the space around them, creating a physical reality in the region between objects that exert forces on each other. Faraday's field concept was initially regarded with skepticism by the mathematical physicists of his day. Faraday had almost no mathematical training. He couldn't write equations. He thought in pictures, in intuitions, in physical models. His contemporaries, trained in the rigorous mathematical traditions of French and German physics, found his field lines charming but imprecise. And then Maxwell came along and showed that Faraday's intuitions were exactly right. Maxwell took Faraday's pictorial field concept and translated it into precise mathematical language. And the mathematics revealed that the fields are not just a useful way of thinking about forces. They are real, physical entities with their own properties, their own dynamics, their own energy. They can vibrate, they can propagate, they can carry energy and momentum through empty space. Light, Maxwell showed, is a vibration of the electromagnetic field that Faraday had intuited. The bookbinder's apprentice from South London, the man with no formal mathematical training, had seen the truth more clearly than anyone with a blackboard full of equations. The field is real. The field is fundamental, and light is what happens when the field vibrates. When Faraday was elderly and his memory was failing, Maxwell visited him and tried to explain, in simple terms, what his equations had revealed about the fields. Faraday reportedly listened carefully and then asked simply whether Maxwell's work confirmed or denied his own ideas about lines of force. Maxwell told him that it confirmed them completely. Faraday was pleased. Faraday died in 1867. Maxwell died in 1879. Neither lived to see Hertz's experimental confirmation of electromagnetic waves in 1886. Neither saw the radio revolution that their work made possible. But the line of intellectual inheritance is as clear as a beam of light. Faraday's physical intuition, translated into Maxwell's mathematics, predicted electromagnetic waves. Hertz confirmed them, Marconi harnessed them, and the entire modern world of wireless communication, from radio to Wi-Fi to satellite navigation, grew from the seed that a bookbinder's apprentice planted in a London laboratory in the 1830s. And the person who took Faraday's intuition and turned it into one of the most beautiful mathematical frameworks in the history of science was about to arrive on the scene. His name was James Clerk Maxwell, and the story of what he discovered is, for my money, one of the most beautiful in all of science. When a young James Clerk Maxwell arrived at the University of Cambridge in 1850, he was told that attendance at the 6 a.m. chapel service was compulsory. Maxwell, who had always been a night owl, reportedly replied, "I suppose I could stay up that late." He was Scottish, born in Edinburgh in 1831, and from an early age, he displayed that combination of deep curiosity and playful wit that would characterize his entire career. He was fascinated by everything, from the physics of Saturn's rings to the behavior of gases to the perception of color. But his crowning achievement, the one that places him alongside Newton and Einstein in the pantheon of physics, was his work on electricity and magnetism. To understand what Maxwell did, you need to know a little about the state of electromagnetic science in the mid-19th century. By the 1850s, physicists had accumulated a rich body of knowledge about electricity and magnetism, but it was scattered across dozens of separate findings and relationships, discovered by different people in different countries over the course of decades. There was no overarching theory, no unified framework. People knew that electric charges exert forces on each other. They knew that magnets attract and repel. They knew, thanks to the Danish physicist Hans Christian Ørsted, that an electric current flowing through a wire creates a magnetic field around the wire. A compass needle placed near a current-carrying wire swings away from north, deflected by this invisible magnetic influence. And they knew, thanks to the English experimentalist Michael Faraday, that the reverse is also true. A changing magnetic field can induce an electric current in a nearby wire. Move a magnet near a loop of wire and a current flows, even though nothing is physically touching the wire. Electricity creates magnetism. Magnetism creates electricity. The two phenomena were clearly linked, entangled with each other in some deep way. But nobody had written down a single unified set of equations that captured all of these relationships in one coherent mathematical framework. Nobody, that is, until Maxwell. What Maxwell did was to take all the known laws and relationships of electricity and magnetism and distill them into a set of 4 equations. Just 4. 4 equations that describe completely and precisely how electric fields and magnetic fields behave, how they're created, how they influence each other, and how they change over time. These 4 equations, now known as Maxwell's equations, are among the most important mathematical statements in the history of physics. And here is where the magic happens. Maxwell didn't just summarize existing knowledge. He noticed something in his equations that nobody had seen before. Think about what we know so far. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Each one generates the other. Now, Maxwell asked a deceptively simple question. What happens if you start with a disturbance in the electric field, out in empty space, far from any wires or magnets or charges? Just a little pinch in the electric field, a local deviation from zero. His equations told him what would happen next. The changing electric field would create a magnetic field nearby. But that new magnetic field would also be changing, because it just appeared out of nothing. And a changing magnetic field creates an electric field, which creates another magnetic field, which creates another electric field. And these disturbances don't just sit still, they propagate outward. They ripple away from the original disturbance like waves on a pond. Electric field creates magnetic field, creates electric field, creates magnetic field. leapfrogging each other, sustaining each other, racing outward through space. Maxwell had discovered, purely from his equations, that electromagnetic disturbances can propagate through space as self-sustaining waves. No medium required. The electric and magnetic fields bootstrap each other, each one regenerating the other as the wave moves forward. The wave carries itself. And then Maxwell calculated the speed of these waves. The speed fell out of his equations as a specific combination of two constants, two numbers that had been measured independently in laboratories through experiments with charged objects and current-carrying wires. One was a number that described how strongly electric fields respond to electric charges. The other described how strongly magnetic fields respond to electric currents. These two numbers had been sitting in physicists' notebooks for years. Nobody had ever suspected they had anything to do with each other, let alone with light. When Maxwell combined them, he got a speed. And that speed was about 300,000 kilometers per second, the speed of light. Maxwell's reaction, as far as we can tell from his writings, was measured but clearly excited. He later wrote that, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena." In plainer language, light is an electromagnetic wave. Think about what that means. Light, the thing that lets you see the world, the stuff that pours out of the sun and bounces off every object around you, is a ripple in the electromagnetic field. An oscillating dance of electric and magnetic energy, each one generating the other, the whole thing racing through space at the cosmic speed limit. When light hits your eye, the oscillating electric field jiggles the electrons in the atoms of your retina, and those jiggling electrons send signals to your brain, and that's what you experience as vision. Maxwell didn't just explain what light is. He unified optics with electromagnetism. Light wasn't a separate phenomenon anymore. It was a special case of something bigger, electromagnetic radiation. And that meant there should be other kinds of electromagnetic waves out there, waves with wavelengths longer or shorter than the tiny sliver that human eyes can detect. There should be electromagnetic radiation that we can't see. Maxwell died of abdominal cancer in 1879, at the age of just 48. He didn't live to see his prediction confirmed, but it was confirmed, spectacularly, just a few years later. In 1886, a young German physicist named Heinrich Hertz, working at the University of Karlsruhe, built a device that could generate electromagnetic waves in the laboratory. His apparatus was crude by modern standards, basically a pair of metal rods with a gap between them. When he applied a high voltage, a spark jumped across the gap, and the sudden burst of current created a pulse of electromagnetic radiation. Across the room, another pair of rods with a gap in them acted as a receiver, and when Hertz watched the receiver, he saw tiny sparks appearing in its gap, triggered by the invisible waves traveling across the room from the transmitter. Hertz had produced and detected electromagnetic waves. He showed that these waves traveled at the speed of light, could be reflected by metal surfaces, and exhibited all the properties of light: refraction, interference, polarization. Maxwell's prediction was vindicated. Light really was an electromagnetic wave. And the waves Hertz had discovered, waves with wavelengths much longer than visible light, would soon change the world in ways that Hertz himself couldn't foresee. When asked about the practical applications of his discovery, Hertz reportedly said, "Nothing, I guess." He was interested in the physics, not the engineering. But within a decade of Hertz's experiments, a young Italian inventor named Guglielmo Marconi was using these very waves to send messages through the air without wires. We call them radio waves now, and they underpin virtually every form of wireless communication in the modern world. Radio, television, Wi-Fi, cell phones, Bluetooth. All of them are Maxwell's electromagnetic waves. All of them are light, just in wavelengths that our eyes can't detect. So, by the end of the 19th century, the wave theory of light had achieved what looked like a total, permanent, irreversible victory. Newton's particles were gone. Light was a wave, an electromagnetic wave, and Maxwell's equations described it with breathtaking precision and elegance. The wave theory could explain reflection, refraction, interference, diffraction, polarization, the entire spectrum from radio waves to visible light to X-rays. The whole thing was wrapped up in 4 beautiful equations. And so, with Maxwell's equations in hand, the understanding of light had reached a level of elegance and completeness that seemed almost too good to be true. But what Maxwell had done wasn't just explain light. He had expanded the very concept of what light is. Before Maxwell, light meant the stuff you can see, the visible spectrum, the rainbow. After Maxwell, light meant electromagnetic radiation of any frequency. And the visible spectrum, the sliver of frequencies that human eyes can detect, turned out to be an absurdly narrow slice of the whole. Think of it like a piano keyboard. If the electromagnetic spectrum were a piano with, say, 60 octaves of keys, the visible spectrum would be less than a single key, 1 key out of 60 octaves. Everything else, from the deep bass rumble of radio waves to the piercing high notes of gamma rays, is invisible to us. We evolved eyes that detect a tiny, tiny fraction of the light that exists. Maxwell's equations predicted the existence of electromagnetic waves beyond the visible, but it took decades for physicists to fill in the full picture. Hertz discovered radio waves in 1886. Wilhelm Röntgen discovered X-rays in 1895, winning the first ever Nobel Prize in physics for the feat. Röntgen's experiments were so surprising that he initially doubted his own results. He spent weeks in his laboratory, alone, checking and rechecking, before he told anyone. And the famous story of how he convinced his wife Bertha to place her hand in the beam, producing the first X-ray photograph of a human body, revealing the bones of her fingers and the ring on her hand, is one of the most iconic moments in the history of science. When Bertha saw the ghostly image of her own bones, she was reportedly horrified, saying something along the lines of having seen her own death. X-rays turned out to have wavelengths thousands of times shorter than visible light, so short that they can pass through flesh but are stopped by bone. The medical applications were obvious and immediately exploited, and within a year of Röntgen's discovery, X-ray machines were being used in hospitals around the world to diagnose fractures and locate foreign objects in the body. The discovery of X-rays also triggered a chain of discoveries that would reshape physics forever. In 1896, Henri Becquerel, inspired by Röntgen's work, was investigating whether fluorescent minerals produced X-rays. He wrapped a photographic plate in dark paper, placed a uranium compound on top of it, and planned to expose the whole thing to sunlight. But the weather was cloudy, so he put the setup in a drawer and forgot about it for several days. When he finally developed the plate, expecting a faint image or nothing at all, he found it was strongly exposed. The uranium had fogged the plate without any sunlight. Something was coming out of the uranium on its own, spontaneously, with no external energy source. Becquerel had discovered radioactivity, and the radiation he had discovered turned out to include gamma rays, the highest frequency electromagnetic radiation of all, with wavelengths smaller than the nucleus of an atom. Marie Curie, working with her husband Pierre, dove into the study of radioactivity with legendary dedication. In a leaky shed that served as their laboratory, Marie spent years processing tons of uranium ore by hand, stirring massive vats of boiling, chemically treated rock with an iron rod almost as tall as she was. She was searching for the source of the mysterious radiation, and eventually she isolated 2 new elements: polonium, named for her native Poland, and radium. The work was physically grueling and, as we now know, extremely dangerous. Marie Curie's laboratory notebooks are still so radioactive that they're kept in lead-lined boxes, and anyone who wants to consult them must wear protective gear. Curie received 2 Nobel Prizes, the first in physics in 1903, shared with Pierre and Becquerel for their work on radioactivity, and the second in chemistry in 1911 for her discovery of radium and polonium. She remains the only person in history to win Nobel Prizes in 2 different sciences. And so, by the early 20th century, the electromagnetic spectrum had been mapped out from radio waves to gamma rays. Every type of electromagnetic radiation, from the lowest frequencies to the highest, obeyed Maxwell's equations. Every type traveled at the same speed in vacuum. Every type exhibited interference, diffraction, and polarization. The wave theory of light, extended to include all electromagnetic radiation, seemed to be complete, final, and unassailable. But it wasn't. Because even as physicists were filling in the last gaps of the electromagnetic spectrum and congratulating themselves on a job well done, 3 stubborn little experiments were whispering that something was very, very wrong. The black body spectrum didn't fit. The photoelectric effect didn't work. And when blue light hit metal, electrons came off instantly, which made no sense if light was a smooth, continuous wave. The cracks were small, but they were real, and they were about to bring the whole edifice down. There is another chapter in the measurement of light's speed that deserves telling, because it connects to the ether question in a way that would prove fatally important. In the early 19th century, with the wave theory gaining momentum, the question of what medium carries light waves became urgent. If light is a wave in the ether, then the ether must exist, and the Earth must be moving through it. And if the Earth is moving through the ether, then the speed of light should be slightly different depending on which direction you measure it. Light traveling in the same direction as the Earth's motion through the ether should appear a little slower, like swimming upstream. Light traveling in the opposite direction should appear a little faster, like swimming downstream. The expected difference was tiny, a fraction of a percent, because the Earth's orbital speed is only about 30 kilometers per second, roughly 1/10,000th of the speed of light. Detecting such a small difference would require an extraordinarily sensitive experiment, and that's exactly what Albert Michelson set out to build. Michelson was obsessed with precision. Born in Prussia in 1852, he emigrated to America as a child and eventually enrolled at the United States Naval Academy. He became fascinated with the measurement of the speed of light during his time at the Academy, and this fascination would dominate his entire career. He refined his measurements over decades, improving the accuracy each time, and in 1907, he became the first American to receive the Nobel Prize in Physics, specifically for his optical instruments and the measurements he made with them. But his most important experiment was not a measurement of the speed of light itself. It was a measurement of the difference in the speed of light in 2 perpendicular directions. The Michelson-Morley experiment of 1887. Michelson designed and built an instrument called an interferometer, a device that splits a beam of light in 2, sends the 2 halves along perpendicular paths of equal length, and then recombines them. If the 2 beams travel at exactly the same speed, they arrive back in sync and produce a bright, featureless pattern. But if one beam is even slightly faster or slower than the other, the 2 waves arrive slightly out of step, and the recombined light shows a pattern of light and dark fringes, an interference pattern. The instrument was sensitive enough to detect speed differences far smaller than the expected ether effect. Michelson mounted it on a heavy stone slab floating in a trough of mercury, allowing the entire apparatus to be rotated smoothly. If the ether existed, and if the Earth was moving through it, then rotating the interferometer should change which arm was aligned with the ether wind, and the fringe pattern should shift. Michelson teamed up with Edward Morley, a meticulous chemist, and together they ran the experiment. They rotated the interferometer. They tested at different times of day. They repeated the experiment in different seasons when the Earth's velocity through space points in different directions. The result was always the same. No fringe shift, no difference. The speed of light was identical in every direction, to within the precision of the instrument. The ether wind simply wasn't there. Michelson was reportedly disappointed. He had expected to detect the ether and had designed the most sensitive instrument in the world to do so. Finding nothing felt like a failure. He referred to the experiment as this beautiful and delicate experiment, but seemed to view the null result as a personal defeat rather than a scientific breakthrough. And yet, it was a breakthrough of the highest order. The Michelson-Morley null result was one of the key experimental facts that led Einstein to special relativity. If the speed of light is the same in all directions, regardless of the Earth's motion, then either the ether doesn't exist, or the Earth is somehow always at rest with respect to it, which would mean the entire Copernican revolution was wrong and the Earth really is the center of the universe. Nobody was willing to accept that second option, so the ether had to go. Lorentz and Fitzgerald tried to save it by proposing that objects physically contract in the direction of their motion through the ether, by precisely the amount needed to cancel out the expected effect. This explained the null result, but it felt like a cheat, a theory propped up by an ad hoc assumption designed to make it match the data. Einstein took a different approach entirely. He didn't try to explain why the ether wind was undetectable. He simply declared that there is no ether wind, because there is no ether. And the speed of light is the same for all observers, not because of some conspiracy of compensating effects, but because that's how the universe actually works. The invariance of the speed of light isn't a puzzle to be explained. It's a fundamental fact to be accepted. And if you accept it, and work out the consequences with mathematical rigor, you arrive at the theory of special relativity, with all its famous predictions about time dilation, length contraction, and the equivalence of mass and energy. The Michelson-Morley experiment didn't directly inspire Einstein's 1905 paper. Einstein's own accounts of how he arrived at special relativity focus more on thought experiments about what you'd see if you chased a beam of light. But the experiment provided the crucial empirical foundation. It showed that the invariance of light speed is not just a theoretical nicety, it's an experimental fact, and it killed the ether. After 2 centuries of assuming that light needs a medium to travel through, physics finally accepted that light propagates through empty space, needing nothing, requiring no substance to vibrate, no scaffolding to support it. The electromagnetic field carries itself, and the speed at which it does so is a feature of space-time, not of any medium. This was a profound shift in how physicists think about physical reality. Before the Michelson-Morley experiment, space was thought to be filled with a substance, the ether, that provided the stage on which electromagnetic phenomena played out. After the experiment, and after Einstein, space itself became the stage, with no substance required. And eventually, with quantum field theory, even the notion of empty space would be revealed as an illusion, because the quantum fields that fill all of space-time are always there, always fluctuating, always buzzing with virtual particles that pop in and out of existence. The vacuum, it turns out, is the most complex and dynamic entity in physics, and light, far from needing a medium to travel through, is itself an excitation of one of those vacuum fields. Light doesn't travel through something. Light is something, a ripple in a field that is everywhere and always. And the mood in physics at the time was, honestly, a little smug. There was this widespread feeling, especially among the older generation of physicists, that the big questions had mostly been answered. Newton had given us mechanics and gravity. Maxwell had given us electromagnetism and light. Thermodynamics was well understood. Lord Kelvin reportedly said that there was nothing new to be discovered in physics, that all that remained was more and more precise measurement. The grand architecture was done, they were just polishing the furniture. They could not have been more wrong, because there were a few stubborn little problems lurking at the edges. Small things that didn't quite fit. experiments that gave results nobody could explain using the physics they had. And one of those problems, one of those tiny, annoying cracks in the otherwise perfect edifice of 19th century physics, had to do with the way light interacts with metal. And that crack was about to blow the whole thing wide open. But before Einstein and his photons could upend the wave theory, there was another problem brewing. One that would provide the first hint that something was deeply wrong with classical physics. And this problem had nothing to do with beams of light or slits in a wall. It was about something much more mundane. It was about how hot things glow. You've seen this yourself. Think about a piece of metal in a blacksmith's forge. As it heats up, it starts to glow. First a dull red, then orange, then yellow, then, if you push it far enough, a brilliant white. The color changes with the temperature. This is called black-body radiation, and by the 1890s, physicists had very carefully measured exactly how much energy a hot object radiates at each color, at each frequency of light. They had beautiful, precise, experimental curves showing this relationship. And then they tried to explain those curves using classical physics, using Maxwell's equations. And they got a prediction that was absolutely, catastrophically wrong. Here's what happened. The classical calculation, worked out carefully by Lord Rayleigh and James Jeans, predicted that a hot object should radiate more and more energy at higher and higher frequencies. As you move from red to violet to ultraviolet and beyond, the energy should just keep climbing, going to infinity. Infinite energy pouring out of every warm object. Your coffee mug would be bathing you in lethal ultraviolet radiation. Your own body would be a death ray. Everything warm would be radiating infinite energy at the ultraviolet end of the spectrum. This was so obviously, spectacularly wrong that it got a wonderfully dramatic name, the ultraviolet catastrophe. And it wasn't a small error or a minor discrepancy. The theory predicted infinity where the experiments showed a gentle curve that peaked and then fell off. Something was fundamentally broken in the classical picture. And this is where a quiet, methodical, deeply conservative German physicist enters the story. His name was Max Planck. Planck was born in 1858 in Kiel, Germany. He was not the kind of person you'd expect to start a revolution. He was orderly, traditional, a man of routine. He loved thermodynamics the way some people love a well-tended garden. The structure, the order, the elegance of the laws. One of his professors, Philip von Jolly, actually advised the young Planck against going into physics, telling him that the field was essentially complete and that there was nothing important left to discover. Planck reportedly responded that he didn't want to discover new things. He just wanted to understand the existing foundations more deeply. The irony of this is almost painful, because this cautious, conservative man ended up blowing a hole in those foundations that physics has never recovered from. In the year 1900, Planck was working on the black-body radiation problem. He was trying to find a mathematical formula that would match the experimental data, and he found one. He found a formula that fit the data perfectly. Every feature of the experimental curve, the rise at low frequencies, the peak, the fall-off at high frequencies, was captured precisely by Planck's formula. But to make his formula work, he had to make a strange assumption. He had to assume that the atoms in the walls of the hot object could only emit or absorb energy in discrete chunks, in specific, indivisible amounts. Not any amount, but only whole number multiples of some tiny basic unit. He called these chunks quanta, from the Latin word for how much. The size of each quantum depended on the frequency of the radiation. Higher frequency meant larger quanta, and the relationship was simple. The energy of one quantum equals the frequency multiplied by a tiny constant, a number so small that in everyday life you'd never notice the chunkiness. Planck called this constant h. We call it Planck's constant. Think about what this means. In classical physics, energy is smooth, continuous. You can have any amount of it. It's like water. You can pour a glass, or a half glass, or a tenth of a glass, as fine-grained as you want. What Planck was saying is that at the atomic level, energy is more like sand. From a distance it looks smooth, but up close it comes in tiny individual grains. You can have 1 grain, or 2 grains, or 100 grains, but never 1 1/4. And this solved the ultraviolet catastrophe. At high frequencies, the quanta become so large that atoms can't easily emit them. The energy staircase has steps that are too tall to climb. So the amount of radiation emitted at high frequencies drops off, exactly as the experiments showed, instead of shooting off to infinity. But Planck himself didn't believe this was how nature actually worked. He thought it was a mathematical trick, a convenient fiction that happened to give the right answer. He spent years trying to find a way to derive his formula using purely classical physics, without the quantum assumption. He never could. He called his introduction of the quantum an act of desperation. Those are his actual words. He expected someone would eventually find a proper classical explanation. Nobody ever did. And it was 5 years later, in 1905, that Einstein took Planck's cautious, reluctant idea and pushed it to its radical conclusion. Planck had quantized the oscillators in matter, the atoms. Einstein went further. He quantized light itself. He said the light doesn't just get emitted in chunks. The light itself is chunks. Each chunk is a photon, and each photon carries exactly 1 quantum of energy, determined by the frequency. This was a much bolder claim, and as we've already seen, it was deeply controversial. But it explained the photoelectric effect perfectly, and it was the beginning of the quantum revolution that would consume physics for the next century. The problem was called the photoelectric effect, and on the surface it seemed like it should be simple to explain. When you shine light on certain metals, electrons pop off the surface. The light's energy knocks the electrons loose, the way a wave washing over a beach might dislodge pebbles from the sand. Simple enough. But the details were wrong. The way the electrons came off didn't match what Maxwell's wave theory predicted, and the mismatch was specific and consistent and impossible to ignore. Here's what Maxwell's theory said should happen. Light is a continuous wave of electromagnetic energy. Brighter light carries more energy. So if you shine a brighter light on the metal, the electrons should come off with more energy, moving faster. Crank up the brightness, get faster electrons. And if you dim the light, it should take longer for enough energy to build up to knock electrons free. Dim light, slow electrons, delayed emission. That all makes sense if light is a smooth, continuous wave, washing energy onto the surface a little at a time. But here's what actually happened in the experiments. The energy of the ejected electrons didn't depend on the brightness of the light at all. Not at all. You could shine an incredibly bright red light on the metal, as bright as you wanted, and no electrons would come off. Zero. No matter how long you waited. But a dim violet light, barely a whisper of illumination, would start knocking electrons off immediately, and those electrons would come off with significant energy. What mattered wasn't the brightness. What mattered was the color. Blue light produced energetic electrons. Green light produced less energetic ones. Red light produced none. Cranking up the brightness of the red light didn't help. Even a flood of red photons couldn't do what a trickle of blue photons could. And the emission was instantaneous. There was no build-up time, no gradual accumulation of energy. The moment you turned on a violet light, electrons started coming off. This made absolutely no sense in Maxwell's framework. If light is a continuous wave, then all colors of light carry energy, and brighter means more energy. A sufficiently bright red light should eventually deliver enough energy to knock electrons free, even if each individual wave crest carries less energy than a blue one. You just need more crests, more waves, more time. But the experiment said no. Red light, no matter how intense, simply couldn't do it. something was deeply wrong. The year was 1905, and the person who solved the puzzle was a 26-year-old patent clerk in Bern, Switzerland, who had been unable to find an academic position and was doing physics in his spare time. You already know his name, Albert Einstein. And the solution he proposed would earn him the Nobel Prize, though not for another 16 years. Einstein's answer was radical, and it went directly against everything Maxwell had established. Einstein said that light is not a continuous wave when it interacts with matter. Instead, the energy of light is concentrated in discrete packets, individual bundles, each one carrying a specific amount of energy. The energy of each packet depends on the frequency of the light, which is related to its color. High-frequency light, like violet or blue, comes in packets with lots of energy. Low-frequency light, like red, comes in packets with less energy. When light hits a metal surface, each packet interacts with a single electron. One packet, one electron, one interaction. If the packet carries enough energy to overcome the forces holding the electron in the metal, the electron pops free. If it doesn't, nothing happens. No amount of low-energy packets can substitute for one high-energy packet because each interaction is individual and discrete. 1,000 gentle taps can't do what one firm knock can. This explained everything. Red light fails to eject electrons because each red packet simply doesn't carry enough energy, no matter how many of them arrive. Blue light succeeds because each blue packet carries enough energy to do the job. Brighter light means more packets arriving per second, which means more electrons popping off, but each electron comes off with the same energy, because each one is freed by a single packet with the same energy as all the others. The emission is instantaneous, because there's no build-up. The moment a sufficiently energetic packet arrives, bang, the electron is free. No waiting, no accumulation. These packets of light energy didn't have a name yet in 1905. Einstein called them light quanta. The word photon wouldn't be coined until 1926, when the American chemist Gilbert Lewis introduced it in an article in the journal Nature. But the concept was already there in Einstein's 1905 paper. Light, when it interacts with matter, behaves as if it's made of particles. Sit with that for a moment. For a century, the wave theory had been triumphant. Young's interference, Fresnel's diffraction, Maxwell's equations, Hertz's radio waves, an overwhelming mountain of evidence that light is a wave. And now Einstein was saying that actually, when you look at how light interacts with electrons, it behaves like a particle. Like Newton's corpuscles, reborn. Einstein himself was very clear about how radical this was. He knew he was challenging Maxwell, and Maxwell's equations were the crown jewel of 19th century physics. The photoelectric paper was, in a way, even more revolutionary than his paper on special relativity, published the same year. Relativity extended and refined the existing framework. The photoelectric paper broke it. And here's what's fascinating about Einstein and the Nobel Prize. When the Nobel Committee finally awarded Einstein the prize in 1921, the citation read, "For his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect." Not for relativity. For the photoelectric effect. Because the photoelectric effect was what had been experimentally confirmed beyond doubt by that point. And because, in many ways, it was the more disruptive contribution. It was the one that cracked open quantum mechanics. But the physics community did not embrace Einstein's light quanta quickly or easily. Even Max Planck, who had himself introduced the idea of quantized energy in 1900 while working on a different problem, the spectrum of heat radiation, thought Einstein had gone too far. Planck had quantized the oscillators in matter, the atoms in the walls of a heated cavity. That was strange enough. But Einstein was quantizing light itself. He was saying that electromagnetic radiation, this thing Maxwell had shown was a continuous wave, actually has a particle-like nature. It comes in lumps. When Planck wrote a letter recommending Einstein for the Prussian Academy of Sciences in 1913, he praised Einstein's many contributions, but specifically noted that Einstein had sometimes missed the target in his speculations, citing the light quantum hypothesis as an example. Planck was essentially saying, "Great physicist, but that photon thing is probably wrong." It wasn't wrong, and the evidence kept piling up. In 1923, an American physicist named Arthur Compton performed an experiment that put the particle nature of light beyond serious doubt. Compton aimed a beam of X-rays at a target of carbon atoms. X-rays are just electromagnetic radiation with a very short wavelength, far shorter than visible light. When the X-rays hit the carbon atoms, some of them bounced off, scattered in various directions. Compton carefully measured the wavelength of the scattered X-rays and compared it to the wavelength of the incoming ones. If X-rays were purely waves, the scattered waves should have had the same wavelength as the incoming ones, maybe slightly modified by some continuous process. But that's not what Compton found. The scattered X-rays had a longer wavelength than the incoming ones, and the amount by which the wavelength changed depended on the angle at which the X-ray bounced off. Compton realized that the only way to explain this result was to treat the interaction as a collision between two particles, the X-ray photon and an electron in the carbon atom. The X-ray photon comes in, hits the electron, bounces off in a new direction, and in the collision transfers some of its energy and momentum to the electron. The photon loses energy in the collision, and since the energy of a photon is related to its frequency, losing energy means the frequency drops and the wavelength gets longer. The mathematics of the collision worked perfectly when Compton treated the X-ray as a particle with a specific energy and momentum, exactly the way you'd treat a billiard ball hitting another billiard ball. He couldn't make the numbers work using Maxwell's wave picture. The X-rays were acting like particles, period. Compton's experiment was so clean and so decisive that it essentially ended the debate about whether light has a particle-like aspect. After 1923, no serious physicist doubted that light quanta were real. Compton received the Nobel Prize for his work in 1927. So, the pendulum had swung again, from wave back to particle. Newton's corpuscles were back, in a new and more sophisticated form. Light comes in packets, in photons, and when it interacts with matter, it interacts as a particle. But wait, if light is a particle, then how do you explain interference? How do you explain Young's double-slit experiment? How do you explain all those beautiful, unambiguous, absolutely ironclad demonstrations of wave behavior that had been accumulating for over a century? Because those experiments hadn't gone away. They were still there. The interference patterns were still there. And they still couldn't be explained by particles. By the mid-1920s, physicists were in a genuinely uncomfortable position. They had two sets of experiments that seemed to flatly contradict each other. One set, interference, diffraction, polarization, showed beyond any doubt that light is a wave. The other set, the photoelectric effect, Compton scattering, showed beyond any doubt that light is a particle. Both sets of experiments were clean, repeatable, and well understood. And yet, they couldn't both be right. Or could they? The famous physicist Sir William Lawrence Bragg summed up the confusion with a quip that has been repeated ever since. On Mondays, Wednesdays, and Fridays, we use the wave theory. On Tuesdays, Thursdays, and Saturdays, we think in streams of flying energy quanta or corpuscles. It was a joke, but it captured the genuine bewilderment of the physics community. How could the same thing be both a wave and a particle? Those are contradictory categories. A wave is spread out, continuous, extended in space. A particle is concentrated, discrete, localized. You can't be both. That's like saying something is both a noun and a verb. The categories are mutually exclusive. Except, apparently, they aren't. Because light didn't care about human categories. Light did what it did. And if human concepts weren't up to the task of describing it, that was a problem with the concepts, not with the light. The resolution, when it came, would be more disturbing than either side had imagined. And it started with a question from a French prince who had a very unusual idea about electrons and waves. Louis-Victor Pierre Raymond de Broglie was born into one of the most aristocratic families in France in 1892. The de Broglie family had been prominent in French politics, diplomacy, and the military for centuries, and Louis held the hereditary title of Duke. He originally studied history at the Sorbonne, planning a career in the humanities, but his older brother Maurice was a physicist working on X-rays, and something about the family dinner table conversations about radiation and atoms pulled Louis into physics. By the early 1920s, de Broglie was working on his doctoral thesis, and the question he kept turning over in his mind was audacious in its simplicity. Everyone was arguing about whether light is a wave or a particle. Einstein had shown that light, traditionally understood as a wave, also has particle-like properties. So, de Broglie asked, what if the reverse is also true? What if matter, traditionally understood as particles, also has wave-like properties? Think about how bold that suggestion is. An electron is a tiny speck of stuff with mass and electric charge. You can deflect it with a magnet. It leaves tracks in cloud chambers. It behaves, in every obvious way, like a particle, like a tiny bullet. And de Broglie was saying that this thing also has a wavelength, that it ripples, that it can interfere with itself, just like light passing through Young's double slit. De Broglie didn't just suggest it vaguely, he wrote down a formula. The wavelength of any particle, he said, is equal to Planck's constant divided by the particle's momentum. Simple, clean, elegant. For anything you can hold in your hand, a baseball, a grain of sand, even a bacterium, the mass is so large compared to Planck's constant that the wavelength comes out absurdly small, trillions of times smaller than an atomic nucleus. You'd never notice it. The wave nature of everyday objects is real in principle, but completely invisible in practice. But for something as light as an electron, moving at the kinds of speeds electrons move at inside atoms, the wavelength turns out to be on the order of the size of an atom. And at that scale, the wave nature isn't a footnote, it's the main event. De Broglie submitted his thesis in 1924. The story goes that his thesis committee wasn't entirely sure what to make of it. The idea was elegant, even beautiful, but it was also claiming that everything made of matter is also a wave, and that's not the kind of thing you just nod along with. One of the committee members sent the thesis to Einstein for a second opinion, and Einstein reportedly replied that de Broglie had lifted a corner of a great veil. That was enough. The thesis was accepted, and in 1927, the prediction was experimentally confirmed. Clinton Davison and Lester Germer, working at Bell Labs in New York, fired electrons at a nickel crystal and observed a diffraction pattern. The electrons were scattering off the regularly spaced atoms in the crystal in exactly the way that waves scatter off an array of obstacles. The electrons were behaving as waves. Independently, George Paget Thomson showed electron diffraction through thin metal films. And here's the historical detail that makes this story almost too perfect. George Thomson was the son of J.J. Thomson, the physicist who had discovered the electron as a particle in 1897. The father won a Nobel Prize for proving the electron is a particle. The son won a Nobel Prize for proving the electron is a wave. Both were right. De Broglie won the Nobel Prize in 1929 for his wave-particle duality hypothesis. And his insight transformed the debate about light from a specific argument about one particular phenomenon into something much larger, much deeper, and much stranger. The problem wasn't just about light anymore. Everything exhibited wave-particle duality, photons, electrons, protons, even whole atoms and molecules. Experiments would eventually show that molecules as large as Buckminster fullerene, 60 carbon atoms arranged in a soccer ball shape, could produce interference patterns. The wave nature of matter isn't limited to subatomic particles. It's universal. We just don't notice it for big objects because the wavelengths are so incredibly small. And so, the centuries-old question, is light a wave or a particle, turned out to be the wrong question. Not wrong in the sense of being unimportant, it had driven enormous progress, but wrong in the sense of presenting a false choice. Light isn't a wave, light isn't a particle. Light is something else. Something that doesn't have a name in everyday language. Something that shows you one face or the other, depending on how you look at it. When you set up an experiment to test for wave properties, interference, diffraction, light dutifully shows you wave properties. When you set up an experiment to test for particle properties, the photoelectric effect, Compton scattering, light dutifully shows you particle properties. But asking, which one is it really, is like asking whether a cylinder is really a circle or really a rectangle. It depends on which direction you're looking from. The cylinder is neither and both, and so is light. This was the birth of quantum mechanics, and the implications were far stranger than anyone expected. To see just how strange, we need to go back to the double-slit experiment. Because when physicists in the 20th century repeated Young's experiment with modern equipment, what they found didn't just challenge their understanding of light, it challenged their understanding of reality. Here's what happened. By the mid-20th century, experimental techniques had advanced to the point where physicists could emit single photons, one at a time. Not a beam of light, not a wave, just individual, discrete photons, fired like tiny bullets at a barrier with two slits. Now, when you fire a single photon at the barrier, it goes through one slit or the other and hits a detector on the far side. And the detector registers the arrival of that photon at a single, specific point. One dot on the detector. The photon behaves like a particle. It arrives at one location, not spread out, not blurry. A definite point of impact. But here's where it gets unsettling. Fire one photon after another, each one individually, each one arriving as a particle at a definite point, and gradually, over hundreds and thousands of individual dots, a pattern starts to emerge on the detector. It's the interference pattern. Young's interference pattern. Bright bands where many photons land, dark bands where almost none do. Think about what that means. Each individual photon is going through the slits alone. There are no other photons for it to interfere with. There's nobody else in the room. And yet somehow each photon knows where to land, such that the collective pattern of many individual arrivals builds up into an interference pattern that only makes sense if each photon went through both slits simultaneously and interfered with itself. A single photon, going through two slits at once, interfering with itself, and then landing at a single definite point, as if it were a particle all along. If you find this difficult to picture, you're in good company. Richard Feynman, one of the greatest physicists of the 20th century, called the double-slit experiment the central mystery of quantum mechanics. He said that it contains the only mystery and that nobody truly understands it. But wait, there's more. Because physicists, being physicists, tried to figure out which slit the photon actually went through. They placed detectors at the slits to catch the photon in the act, to watch it go through one slit or the other. When they did this, the interference pattern disappeared. When the photons were observed at the slits, each one went through one slit or the other, behaving like a well-behaved particle, and the pattern on the far detector was just two bands, one behind each slit. No interference. The wave behavior vanished the moment someone looked, and when they turned the slit detectors off, stopped watching, the interference pattern came back. The wave behavior returned as soon as nobody was checking. Light cares about being observed. When nobody is watching, it travels as a wave, taking all possible paths, going through both slits simultaneously, interfering with itself. When someone checks, it snaps into a definite state, becomes a particle, picks one slit, and acts as if it had been a particle all along. These are not metaphors or philosophical interpretations. The experiments show this repeatedly, consistently, with photons, with electrons, with atoms, with molecules. The act of observation changes the outcome. Now, to be clear, observation here doesn't mean a human being peering at the experiment. It means any physical interaction that could, in principle, reveal which slit the photon went through. It could be a machine doing the detecting. There doesn't need to be a conscious observer. What matters is whether information about the photon's path exists anywhere in the physical world. If it does, the photon behaves like a particle. If it doesn't, the photon behaves like a wave. This is the heart of quantum mechanics, and it is, frankly, bewildering. The best interpretation that physicists have come up with is that between measurements, between observations, a quantum object like a photon doesn't have a definite state at all. It exists in what's called a superposition, a kind of probabilistic blur where all possible states coexist simultaneously. The photon doesn't go through slit A or slit B. It goes through both, or neither. The question, which slit did it go through, doesn't have an answer until the photon is observed, because the photon itself doesn't have a definite path until the observation forces it to choose. When the observation happens, the superposition collapses. The blur sharpens. The photon snaps into a definite state, at a definite location, behaving like a particle. And the probability of finding it at any particular location is governed by the wave function, a mathematical object that evolves like a wave, spreading out, interfering, diffracting, but whose square gives you the probability of the particle showing up at each point. So, in a deeply strange way, both camps in the centuries-old debate were right, and both were wrong. Light travels like a wave, its probability wave spreading out and interfering, but it arrives like a particle, snapping into a definite location at a definite moment. The wave is real, the particle is real. But they're not two different things competing for the title of what light really is. They're two aspects of one deeper thing, something for which we don't have a good everyday word, something that quantum physicists just call a quantum object. We asked for 300 years, wave or particle? And the universe answered, yes. There's a beautiful way to illustrate just how strange this wave-particle duality really is, and it involves nothing more exotic than a pair of sunglasses and a spare lens. You might know that polarizing sunglasses work by blocking certain orientations of light. The lenses contain long chains of molecules aligned in one direction, and they absorb any light that oscillates along that direction, while letting through light that oscillates perpendicular to it. The result is that roughly half the light gets through, and the glare from horizontal surfaces, which tends to be horizontally polarized, gets killed. Now, take two polarizing lenses and hold them up together with their polarization axes at right angles to each other. No light gets through. Every photon that makes it past the first lens is oriented in exactly the wrong direction for the second lens. Total darkness, zero light transmission. But now take a third lens and slip it between the other two, oriented at a 45-degree angle to both. Common sense says that adding more material in the way should block even more light. You've added another obstacle. How could the result be more light getting through? And yet, light reappears. Some photons are now making it through all three lenses. Adding a third barrier has increased the total transmission from 0 to something above 0. How is that possible? The answer is quantum mechanical, and it reveals something deep about the nature of light. When a photon arrives at the first lens with a random polarization, it has a 50% chance of making it through, snapping into the polarization axis of that lens. If it survives, it hits the middle lens, which is at 45 degrees to the first. the photon now has a 50-50 chance of snapping to this new orientation. If it makes it, it hits the third lens, which is again at 45 degrees to the middle one. Another 50-50 chance. The key is that the photon doesn't have a fixed, predetermined polarization that it stubbornly maintains throughout. Each lens forces a new measurement, a new question: are you aligned with me or not? And the photon answers probabilistically, rolling a quantum die each time. If it makes it through the first lens, it doesn't remember its original polarization. It has adopted the new one. And that new polarization gives it a chance of passing the middle lens, which gives it a chance of passing the final lens. Without the middle lens, the jump from the first lens's orientation to the last lens's orientation was 90 degrees, and the probability was 0. With the middle lens providing a stepping stone at 45 degrees, the cumulative probability is no longer 0. The middle lens doesn't block light. It gives the photon a chance to gradually rotate its polarization, step by step, through the full 90 degrees. Light doesn't remember its history. It only knows what's being asked of it right now. It's quantum. It's probabilistic. It snaps to discrete values when measured, and honestly, we don't fully understand why. We can describe the behavior mathematically with exquisite precision. The predictions of quantum mechanics have been confirmed to more decimal places than any other theory in the history of science. But the question of what's really happening, why the photon behaves the way it does, what it's doing between measurements, those questions remain open. And that brings us to the next chapter of our story, because the strangeness of quantum mechanics didn't stop with wave-particle duality and probabilistic measurements. To make sense of all this, to build a mathematical framework that could actually predict the outcomes of experiments with stunning accuracy, physicists had to develop an entirely new kind of theory. And the version of that theory that deals specifically with light, with photons and their interactions with electrons, would turn out to be the most precisely tested scientific theory in all of human history. The person who cracked the code, who built the mathematical machinery that finally explained how light and matter interact at the deepest level, was a quiet, socially awkward English physicist whose equation is carved on a stone in Westminster Abbey, a few feet from Isaac Newton's tomb. To understand what Dirac was trying to do, and why his equation was such a triumph, we need to spend a moment with the quantum revolution that preceded him, because the period between 1925 and 1927 was perhaps the most concentrated burst of intellectual creativity in the history of science. In the summer of 1925, a young German physicist named Werner Heisenberg was suffering terribly from hay fever. He retreated to the rocky North Sea island of Helgoland, where the lack of pollen gave him some relief. And there, working alone through long nights, scribbling calculations in the small hours, he produced a paper that would reshape physics. Heisenberg's approach was radical. He said, "We cannot observe what an electron is doing inside an atom. We cannot watch it orbit. We can only observe what comes out, the light it emits, the frequencies and intensities of spectral lines. So why not build a theory based entirely on observable quantities? Forget about electron orbits. Forget about what the electron is doing between measurements. Just describe the relationships between things we can actually measure." The mathematics Heisenberg used to do this turned out to be matrix algebra, a branch of mathematics that Heisenberg himself wasn't entirely familiar with. His mentor, Max Born, recognized the mathematical structure and helped formalize it. The result was matrix mechanics, the first complete formulation of quantum theory. Within months, the Austrian physicist Erwin Schrödinger produced a completely different formulation of quantum mechanics, one based on waves rather than matrices. Schrödinger's equation describes how a wave function evolves over time, where the wave function encodes the probability of finding a particle at any given location. His approach was more intuitive and more familiar to physicists trained in classical wave theory, and it quickly became the preferred formulation. For a while, physicists were confused. Were there two different quantum theories? Were they compatible? It was soon shown, by both Schrödinger and others, that the two formulations are mathematically equivalent. They're different languages describing the same physics. Matrix mechanics and wave mechanics are two windows onto the same quantum world. And then Heisenberg made one more contribution that shook physics to its foundations. In 1927, he published the uncertainty principle. This principle states that there are certain pairs of physical properties, like position and momentum, that cannot both be known to arbitrary precision at the same time. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our instruments, it's a fundamental feature of nature. The universe simply doesn't have definite answers to both questions simultaneously. The uncertainty principle has enormous consequences. It means that the classical picture of a particle following a definite trajectory through space, like a tiny billiard ball tracing a smooth path, is fundamentally wrong at the quantum scale. Particles don't have trajectories, they have probability distributions. They exist in a fog of possibility until they're measured, and the measurement itself disturbs the system. And this uncertainty isn't just about particles. It applies to fields too. The electromagnetic field, the field whose vibrations are photons, is subject to quantum uncertainty. Even in what we think of as a perfect vacuum, the field is never truly at rest. It fluctuates, randomly and ceaselessly, creating virtual particles that pop into existence and vanish again in intervals too short to observe directly. These vacuum fluctuations are not a theoretical curiosity. They have measurable physical consequences. The Casimir effect, first predicted in 1948 and measured with increasing precision in the decades since, is a tiny attractive force between two uncharged metal plates placed very close together in a vacuum. The force arises because the vacuum fluctuations between the plates are different from the fluctuations outside the plates, creating a net pressure that pushes the plates together. The vacuum isn't empty, it's alive with quantum energy. And it was into this revolutionary landscape that Dirac stepped with his equation, combining the strange new world of quantum mechanics with the strange new world of relativity, and producing predictions that no one had anticipated. His name was Paul Adrien Maurice Dirac, and his story is one of those tales where the peculiarity of the man is matched only by the brilliance of his work. Dirac was born in Bristol, England, in 1902. His father was Swiss-born and taught French at a local school. By all accounts, the household was austere and emotionally cold. Dirac's father insisted that the family speak French at the dinner table, and young Paul, who struggled with the language, learned to say as little as possible. This habit of silence stayed with him for life. His colleagues at Cambridge later joked that the unit of verbal output should be called a Dirac, defined as 1 word per hour. Despite his social difficulties, Dirac was a mind of extraordinary power and originality. He was drawn to the mathematical structure of things, to the abstract patterns beneath the physical world. And in the late 1920s, he turned his attention to a problem that was bothering every physicist working on quantum mechanics. The quantum mechanics that Erwin Schrödinger and Werner Heisenberg had developed in the mid-1920s was a tremendous achievement. Schrödinger's equation described how the wave function of a quantum system evolves over time, and its predictions matched experiments beautifully. But Schrödinger's equation had a limitation. It was built on Newton's framework of space and time, the old framework where time is absolute and space is fixed. It didn't incorporate Einstein's special relativity, which had shown that space and time are flexible, intertwined, and relative. Dirac felt strongly that quantum mechanics needed to be consistent with special relativity. The electron, after all, can move at speeds that are a significant fraction of the speed of light, especially inside atoms. At those speeds, relativistic effects matter. You can't just ignore Einstein when you're doing quantum mechanics. So, Dirac set out to find a quantum equation for the electron that respected special relativity. and after a period of intense work, he found one. The Dirac equation, published in 1928, was a mathematical object of startling elegance. It described the behavior of electrons in a way that was fully compatible with both quantum mechanics and special relativity. And it immediately explained several properties of the electron that had previously been mysterious. For one thing, the Dirac equation automatically predicted that the electron has spin, a quantum mechanical property that makes the electron behave like a tiny bar magnet. Physicists had known about electron spin since the mid-1920s, but it had been added to the theory by hand as an extra assumption. Dirac's equation didn't need the assumption. Spin fell out of the mathematics naturally, as an inevitable consequence of combining quantum mechanics with relativity. But the equation did something else, something no one had anticipated, and it was this that really shook the physics world. The Dirac equation had solutions with negative energy. In the mathematics, there were solutions describing electrons with positive energy as expected, but there were also solutions describing some kind of particle with the same mass as the electron, but with a positive charge instead of a negative one. Dirac initially wasn't sure what to make of these negative energy solutions. For a while, he wondered if they might describe protons. But protons are nearly 2,000 times heavier than electrons, so that didn't work. Eventually, Dirac realized that his equation was predicting the existence of a completely new particle, a particle identical to the electron in every way except for having the opposite electric charge. He called it the anti-electron. We now call it the positron. In 1932, the American physicist Carl Anderson detected exactly such a particle in cosmic ray experiments. The positron was real. Dirac's equation had predicted the existence of antimatter, a prediction confirmed by experiment just 4 years after it was made. Dirac received the Nobel Prize in 1933 at the age of just 31. But the Dirac equation was only the beginning. It described the electron beautifully, but it didn't fully describe how the electron interacts with light, with photons. And developing that description, the full quantum theory of light and its interaction with matter, would take another 2 decades and would involve some of the most difficult and frustrating mathematical challenges in the history of physics. The theory that eventually emerged is called quantum electrodynamics, or QED, and the person most associated with it is a man from Far Rockaway, New York, with a broad Brooklyn accent, a penchant for strip clubs, a love of bongo drums, and one of the most extraordinary minds in the history of science. Richard Feynman was born in 1918, and from a young age, he displayed that particular combination of deep curiosity and irreverent playfulness that would define his entire career. His father, a uniform salesman, encouraged young Richard to ask questions about everything, to never accept an explanation on authority alone, to always work things out from first principles. As a student, Feynman was obviously brilliant, and he was eventually recruited to work on the Manhattan Project at Los Alamos. J. Robert Oppenheimer himself recommended Feynman for a position at Berkeley in a famous letter that said, "He is, by all odds, the most brilliant young physicist here." After the war, Feynman turned his attention to the problem that had been tormenting quantum physicists for years: how to properly describe the interaction between light and matter. The difficulty was this. When physicists tried to use the existing quantum framework to calculate simple quantities, like the energy of a lone electron sitting in its own electromagnetic field, the calculations kept producing infinities. The math blew up. You'd add up all the contributions and the answer would come out as infinity, which is not a physically meaningful result. The problem was related to something called virtual particles. In quantum field theory, the vacuum, what we think of as empty space, is actually seething with activity. Pairs of particles and antiparticles are constantly popping into existence and then annihilating each other, existing for briefer than brief moments, borrowing energy from the universe and paying it back before anyone notices. An electron sitting in space is surrounded by a cloud of these virtual particles. virtual photons, and virtual electron-positron pairs. And when you try to account for all of their effects, the calculation diverges to infinity. Feynman, along with Julian Schwinger in the United States and Shinichiro Tomonaga in Japan, developed a technique called renormalization that tamed these infinities. The basic idea is subtle and somewhat controversial philosophically, but in practice, it works astonishingly well. You identify the infinite parts of the calculation, recognize that they correspond to unmeasurable, bare properties of the particle, and replace them with the measured physical values. What's left is a finite, meaningful prediction that you can compare against experiment. And when they compared the predictions of QED against experiment, the agreement was beyond anything physics had ever seen. Feynman once described the precision by saying that if you measured the distance from Los Angeles to New York, QED's prediction would be accurate to the width of a human hair. The theory predicts the magnetic properties of the electron to better than 10 decimal places. There is no other scientific theory in any field that has been tested to this level of precision and passed. But Feynman's contribution to our understanding of light goes even deeper than the calculations. He developed a way of thinking about quantum interactions that changed how physicists visualize the quantum world. These are the famous Feynman diagrams. A Feynman diagram is a picture, a simple sketch of lines and wiggles that represents a quantum interaction. Straight lines represent particles like electrons. Wiggly lines represent photons. And wherever a straight line and a wiggly line meet, that's a vertex, a point where a photon is emitted or absorbed by an electron. The simplest Feynman diagram for the electromagnetic interaction between two electrons shows two straight electron lines, each with a kink in it, connected by a single wiggly photon line. One electron emits a photon, the other absorbs it, and the exchange of that photon is the electromagnetic force in action. Think about what that means. The electromagnetic force, the force that holds atoms together, that holds your body together, that lets you touch things, that gives rise to chemistry and biology and everything in the material world, is fundamentally just electrons tossing photons back and forth. Two electrons repel other because they're exchanging photons. When trillions of these exchanges happen simultaneously, the cumulative effect looks like the smooth, continuous electromagnetic field that Faraday and Maxwell described. But at the deepest level, there is no field, just particles throwing other particles at each other. And this is where light finally finds its deepest description. In quantum field theory, the framework that encompasses QED, both photons and electrons are understood as excitations of underlying quantum fields. The photon is a ripple in the electromagnetic field. The electron is a ripple in the electron field. These fields permeate all of space, exist everywhere, and their vibrations, their excitations, are what we experience as particles. Think of a still lake. The lake is the field. It's there even when nothing is happening. Now throw a stone. The ripple that spreads outward is the particle. The ripple is not separate from the lake. It is the lake, disturbed, excited, vibrating. Without the lake, the ripple can't exist. And when the ripple dies away, the lake is still there, quiet, waiting for the next disturbance. A photon is a ripple in the electromagnetic field. It's the smallest possible ripple, the minimum possible excitation of the field. You can't have half a photon, just like you can't have half a wave on a guitar string. The field is quantized. Its vibrations come in discrete packets, and those packets are what we call photons. In this picture, the 300-year war between particles and waves dissolves. The question, is light a wave or a particle, finally gets a satisfying answer. Light is neither. Light is a quantized excitation of a field. When you look at the field's behavior as a whole, it looks like a wave, because it is one. It's a ripple in a continuous field that permeates all of space. When you look at the individual excitations, they look like particles because they come in discrete, indivisible packets. Wave and particle are both correct descriptions, but both are incomplete. The full picture is the quantum field. And here's something that should make you pause. The electromagnetic field would exist even if there were no photons at all. Even if nothing were vibrating, the field would still be there, a calm lake waiting to be disturbed. The field is more fundamental than the particles. The particles are just what you get when the field vibrates. This insight extends far beyond light. In the standard model of particle physics, every particle is understood as a vibration in its own quantum field. There's an electron field, a quark field, a neutrino field, and so on. 17 fields in total. Each one fills the entire universe. Each one can vibrate, and when it does, the vibrations show up as particles. The universe, at the most fundamental level we currently understand, is not made of particles embedded in empty space. It's made of fields, overlapping, interacting, quantum fields. And the particles we observe are just the field's way of saying hello. And Feynman had one more strange insight about how photons travel. In the classical picture, Maxwell's picture, a photon is emitted by one electron and absorbed by another. It flies from A to B through space, maybe bouncing off a mirror or passing through a lens on the way, following a definite path. But in Feynman's quantum picture, the photon doesn't take a definite path. It takes all possible paths simultaneously. It goes through the left slit and the right slit. It bounces off every possible surface. It even takes paths that are curved or zigzagging or ludicrously roundabout. Every conceivable route from A to B contributes to the final result. Feynman developed a way to add up all these contributions, called the path integral, or the sum over histories, and the result, the sum of all the crazy paths, gives you the correct quantum mechanical answer. For most paths, the contributions cancel each other out, the way the positive and negative parts of a complicated wave cancel when you add them. Only the paths near the classical straight line path survive the cancellation and contribute significantly. So, in the end, light mostly travels in a straight line, just like you'd expect. But the straight line isn't the only path the photon takes. It's the sum of all paths, with the straight one dominating. And Feynman, working with his mentor John Wheeler, proposed something even more mind-bending about how photons get from A to B. In the traditional picture, an electron in a distant star emits a photon. That photon sails across space for years or centuries or millennia, and eventually another electron in your eye absorbs it. The emission and absorption seem like separate, independent events. But Wheeler and Feynman suggested that they're not independent. The two electrons, the emitter and the absorber, communicate. They handshake across time. The emitting electron sends a signal forward in time, and the absorbing electron sends a signal backward in time. And the photon only exists because both sides agreed on the transaction. This is called the transactional interpretation of quantum mechanics. It's not universally accepted, and it's only one of several competing interpretations of what quantum mechanics really means. But it fits the mathematics perfectly, and it suggests something poetic, that when you look at a distant star on a dark night, an electron in your retina and an electron in the atmosphere of that star have negotiated across the vastness of time and space to exchange a single photon. Now there's one more piece of the story that we need to address, because it connects everything we've talked about and reveals something about the speed of light that most people find genuinely astonishing when they first hear it. We call it the speed of light, 300,000 kilometers per second roughly, 299,792,458 meters per second to be precise. Every photon in the universe, from the faintest radio wave to the most energetic gamma ray, travels at exactly this speed through empty space. But think about how strange that is. The photons from your bedside lamp and the photons from a gamma ray burst billions of light years away carry enormously different amounts of energy. A gamma-ray photon can carry trillions of times more energy than a radio photon. And yet, they all travel at the same speed. In every other context we know, more energy means more speed. Push a car harder, it goes faster. Throw a ball harder, it flies faster. But photons don't work that way. Their energy determines their frequency, their color, but not their speed. Speed is fixed. And it gets stranger. The speed of light is the same for every observer, no matter how they're moving. If you're standing still and you measure the speed of a passing beam of light, you get the same number as someone who's chasing that beam at 90% of the speed of light. Both of you measure the photon moving at exactly the same speed. In everyday life, this never happens. If you're on a moving train and you throw a ball forward, someone on the platform sees the ball going faster than you do because they add the train's speed to the ball's speed. But light doesn't work that way. Light's speed doesn't add to anything. It's always the same number, no matter who's measuring. Einstein built his entire theory of special relativity on this one strange fact. He took it as a starting point, as a fundamental postulate, and worked out the consequences. And the consequences were extraordinary. Time slows down for moving objects, lengths contract, mass and energy are interchangeable. All of these famous results of relativity flow from the single observation that the speed of light is invariant. But why? Why is the speed of light the same for everyone? Why don't faster photons exist? Why does the universe enforce this one specific speed so rigidly? The deepest answer we currently have goes like this. The speed of light is not really a property of light. It's a property of space-time itself. The photon doesn't choose to travel at this speed. The geometry of the universe requires it. The speed of light is the conversion factor between space and time, the number that tells you how much space corresponds to how much time in the fabric of reality. It's baked into the structure of the universe at the most fundamental level. Any massless particle, anything without rest mass, must travel at this speed. Not because of some push or some mechanism, but because the geometry of space-time leaves no other option. A massless thing cannot sit still. It cannot slow down. It cannot speed up. It must move at the invariant speed, always, everywhere, for every observer. Photons happen to be massless, and so they travel at this speed. But if you removed all the photons from the universe, the speed would still exist. It would still be the maximum speed at which any signal, any influence, any causal connection can propagate through the cosmos. Gravitational waves, which are ripples in space-time itself, travel at this same speed. Gluons, the carriers of the strong nuclear force, travel at this speed. The speed is not about light, it's about the universe. Physicists sometimes call it the invariant speed, or the cosmic speed limit, or the speed of causality. Those names capture the truth better than the speed of light, because they make clear that light is just one traveler on a highway that exists independent of any particular vehicle. So, when we measure the speed of light in our instruments, what we're really measuring is a fundamental constant of the universe, a number that encodes the relationship between distance and time in the geometry of space-time. In units where physicists set this speed equal to 1, distance and time are measured in the same units, and Einstein's famous equation simplifies to just energy equals mass. The c squared disappears because it's equal to 1. The number was never about light, it was always about the universe. And there's one last puzzle about the speed of light that's worth mentioning, because it reveals just how slippery and strange this subject can be. In the early 17th century, Galileo tried to measure the speed of light by having two people stand on distant hilltops with lanterns, flashing them back and forth and timing the delay. It didn't work. The delay was too small to measure, and Galileo could only conclude that light's speed was very fast, perhaps infinite. In 1676, the Danish astronomer Ole Romer succeeded where Galileo had failed, by using a much bigger laboratory, the solar system. Römer noticed that the eclipses of Jupiter's moon Io seemed to come early when Earth was closer to Jupiter and late when Earth was farther away. He realized the discrepancy was caused by the finite speed of light. The light from Io's eclipse had to travel a longer distance when Earth was on the far side of its orbit, and that extra distance caused a delay. From the size of the delay and the diameter of Earth's orbit, Römer estimated the speed of light at about 220,000 kilometers per second. Not quite right, but in the right ballpark, and enough to prove that light's speed is finite. Over the following centuries, the measurement was refined. In 1849, Armand Fizeau measured it using a rapidly spinning toothed wheel and a distant mirror. In 1862, Léon Foucault improved the measurement using a rotating mirror. Albert Michelson, in the late 19th and early 20th centuries, devoted much of his career to ever more precise measurements, eventually getting extraordinarily close to the modern value. By the 1970s, the measurement was so precise that scientists decided to flip the logic. Instead of using the definitions of the meter and the second to measure the speed of light, they fixed the speed of light by definition and used it to define the meter. Since 1983, the meter is officially defined as the distance light travels in 1,299,792,458 of a second. The speed of light is no longer a measurement, it's a definition. The number is fixed by decree. But here's the really strange part. All of these measurements, from Römer to Michelson to modern laser experiments, measured the round-trip speed of light. They measured the time it takes for light to go from A to B and back to A. They never measured the one-way speed of light, the time it takes to go from A to B alone. You might think this doesn't matter. Surely the speed is the same in both directions. But try to measure it. To time a one-way trip, you need synchronized clocks at A and B. But how do you synchronize them? You could send a signal from A to B, but that signal travels at the speed of light, and you don't know how long it takes to get there, because that's what you're trying to measure. You could synchronize the clocks at the same location, and then move one of them, but moving a clock changes its rate because of relativistic time dilation. You're stuck in a circular argument. Einstein himself recognized this problem. In his 1905 paper on special relativity, he explicitly noted that the assumption that light travels at the same speed in both directions is a convention, not a measurement. He wrote that it's established by definition, not derived from experiment. The one-way speed of light has never been measured, and there are strong reasons to think it might be fundamentally unmeasurable. This might seem like a minor technical point, but it's actually quite profound. Our most fundamental physical constant, the one we've built our entire system of measurement around, has never been directly measured in one direction. We know the round-trip average, and we assume it's the same both ways. But the assumption is exactly that, an assumption, not a fact. There is something deeply human about the way the speed of light was finally pinned down, because each new measurement required not just better instruments but a bigger laboratory. Galileo's laboratory was 2 hilltops. Römer's was the solar system. Fizeau's was the rooftops of Paris, and Michelson's was a sealed basement with a rotating mirror and a light beam bouncing back and forth across a carefully measured distance. Each experimenter pushed the precision further, but what's remarkable is how consistent the results were once the measurements got good enough. Fizeau, in 1849, got 313,000 kilometers per second. Foucault, in 1862, got 298,000. Michelson, in 1879, got 299,910. By 1950, microwave cavity measurements had it at 299,792.5 kilometers per second. And by the 1970s, laser measurements had pushed the precision so far that the limiting factor was no longer the measurement of the speed, but the definition of the meter itself. That's when physicists made their radical decision. Rather than continuing to refine the speed measurement, they fixed the number and redefined the meter. Since 1983, the speed of light in vacuum is exactly 299,792,458 meters per second, because the meter is defined as the distance light travels in 1/299,792,458 of a second. The speed of light isn't measured anymore, the meter is. This might seem like a circular trick, but it makes deep physical sense. The speed of light is a fundamental constant of nature, more fundamental than any particular unit of length. Nature doesn't know what a meter is. Nature knows the speed of light. By anchoring our system of measurement to light itself, we're aligning our human conventions with the structure of the universe. And there's a philosophical dimension to this that's worth appreciating. For thousands of years, humans defined length by pointing at physical objects. The Egyptian royal cubit was the length of the pharaoh's forearm. The yard was supposedly the distance from Henry I's nose to the tip of his outstretched thumb. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. Later it was defined by a platinum iridium bar kept in a vault in Paris. Each definition was more precise than the last, but each was still tied to a specific physical thing: a body, a bar, a planet. By defining the meter in terms of the speed of light, we've cut the cord to physical objects entirely. Our unit of length is now defined by a universal constant, a number that is the same on every planet, in every galaxy, in every corner of the observable universe. An alien civilization on the far side of the cosmos, if they measured the speed of electromagnetic radiation in their vacuum, would get the same physical constant. Their meter might have a different name and a different numerical value, but the underlying physics would be identical. Light connects everything. It connects stars to eyes. It connects the past to the present. It connects the smallest quantum events to the largest cosmic structures. And now, through our system of measurement, it connects the human world of rulers and clocks to the universal structure of space-time itself. And there is one more experiment worth discussing in detail, because it reveals something about light and observation that goes beyond what we've already covered. It involves the three polarizer paradox, and it is one of the most elegant demonstrations of quantum strangeness you can encounter. Consider a pair of polarizing sunglasses. The lenses are made of thin chains of molecules that run lengthways across the surface, and they absorb any light that oscillates parallel to those chains. Light oscillating perpendicular to the chains passes through freely. The result is that about half the light gets blocked and half gets through. It's a simple filter. Now suppose a single photon arrives at the lens and it happens to be polarized at a diagonal angle, say 45 degrees to the chains. What happens? You might expect the lens to absorb the parallel component and let through the perpendicular component, cutting the photon in half. But photons can't be cut in half. There's no such thing as half a photon. Instead, something much stranger happens. The photon, confronted with the lens, makes a choice. It either passes through entirely, adopting the perpendicular polarization as if it had been that polarization all along, or it gets absorbed entirely. The outcome is probabilistic, a quantum coin flip. At 45 degrees, it's about a 50-50 chance. This is weird enough on its own. But the real strangeness appears when you start stacking lenses. Take two polarizing lenses and orient them at right angles to each other. Hold them up to a light source. No light gets through. Any photon that survives the first lens is polarized in exactly the wrong direction for the second lens. Total darkness. Zero transmission. Now, take a third lens and slide it between the other two, oriented at 45 degrees to both. You've added more material in the path of the light, more stuff blocking the way. Common sense says the result should be even darker, you've added an obstacle. How could more blocking produce more light? And yet, light reappears. Photons are now making it through all three lenses. Adding a barrier has increased the total transmission from 0 to about 12.5%. This defies everyday intuition, but the quantum explanation is surprisingly clean. A photon arrives at the first lens, 50-50 chance of getting through. If it survives, it's now polarized at the first lens's orientation. It hits the middle lens, which is at 45 degrees, another 50-50 chance. If it survives, it adopts the middle lens's orientation. Now it hits the third lens, again at 45 degrees, another 50-50 chance. Half of half of half is 1/8, or 12.5%. The crucial point is that without the middle lens, the photon had 0 chance of getting through the third lens, because the first and third lenses are perpendicular. With the middle lens providing an intermediate step, each photon gets a new chance at each stage. The middle lens doesn't block light. It gives light a chance to progressively rotate its polarization, step by step, through angles that would otherwise be impossible. And this tells us something profound. The photon doesn't remember its history. Each time it encounters a lens, it's confronted with a fresh question. Are you this polarization or not? And it answers probabilistically right then and there. Its past is irrelevant. Its future is undetermined. Only the present measurement matters. This is the essence of quantum mechanics, and light demonstrates it with startling clarity. The photon has no fixed, predetermined identity that it maintains stubbornly through all obstacles. It exists in a state of quantum potential, and each measurement, each interaction, each question the universe asks it, forces it to commit to an answer. An answer that's probabilistic, governed by precise mathematical rules but never certain until the moment it's given. And here is where the story circles back to where it started. You might recall that at the beginning of all this, we talked about the ancient Greeks debating whether light comes from the eyes or from external objects. It seemed like such a simple question, and we resolved it easily. Light comes from outside. But in a strange way, quantum mechanics has reopened a much deeper version of that question. The act of observation matters. When you look at a photon, you change it. When you ask where it is, you force it to be somewhere. When you ask which slit it went through, you force it to have gone through one slit. The observer isn't passive. The act of looking at the world shapes the world that's looked at. The Greeks were wrong about the mechanics. Light doesn't come from your eyes. But they weren't entirely wrong about the relationship between seeing and what is seen. In quantum mechanics, observation and reality are tangled together in a way that is still not fully understood. Now there's one more thread I want to follow before we let this story come to rest. And it has to do with something that connects the very beginning of our narrative to the very end. In the opening of our story, we imagined a photon, a single photon, born in the early universe when the first hydrogen atoms formed, about 380,000 years after the Big Bang. Before that moment, the universe was a dense, opaque fog of plasma, a seething mix of protons, electrons, and photons, all crashing into each other constantly. Light couldn't travel more than a short distance before slamming into a charged particle and being scattered in a random direction. The universe was foggy, opaque, impenetrable to light. But as the universe expanded and cooled, the temperature eventually dropped to the point where electrons could stick to protons and form neutral atoms. Neutral atoms don't scatter photons the way free electrons do. Suddenly, light could travel freely. The fog lifted. The universe became transparent. That transition, from opaque to transparent, released a flood of photons in every direction. Those photons have been traveling ever since, for almost 14 billion years, stretching as the universe expands, losing energy, shifting from visible light all the way down to microwaves. We call them the cosmic microwave background. and they fill the universe uniformly, arriving from every direction in the sky. When you look at the static on an old analog television set, a small fraction of that snow is caused by cosmic microwave background photons striking the antenna. You are literally watching the afterglow of the Big Bang. These photons are the oldest light in the universe. They were among the first to travel freely, and they carry information about what the universe looked like when it was less than 400,000 years old, when it was smaller, denser, hotter, smoother. A universe so different from our own that it barely seems like the same cosmos. And here is a connection that I find almost unbearably beautiful. Those cosmic microwave background photons, the oldest photons we can detect, were born in the same process we've been discussing all along. An electron and a proton came together to form a hydrogen atom, and the energy released in that binding was emitted as a photon. The quantum mechanics of that process, the way the electron transitions between energy levels, the way the photon is emitted, all of it is governed by quantum electrodynamics, by Feynman's diagrams, by the Dirac equation, by the same physics that explains the photoelectric effect and the double-slit experiment and the three-polarizer paradox. The deepest physics of the tiniest interactions produced the oldest light in the universe. The rules of the quantum world, operating at scales trillions of times smaller than a human hair, shaped the cosmos at scales of billions of light years. The very small and the very large are connected through light. And those photons, those ancient travelers, are still governed by the same strangeness we've been exploring. Each one is still a quantum object. Each one still exhibits wave-particle duality. Each one, if you sent it through a double slit, would contribute to an interference pattern. Even after 14 billion years of travel, the quantum nature of light remains unchanged, undiminished, undiluted by time or distance. In a very real sense, the quantum strangeness of light is woven into the structure of the cosmos. The interference patterns that Young saw in 1801 are the same physics that shapes the distribution of galaxies across the sky. The wave-particle duality that confused physicists for 3 centuries is the same phenomenon that governs the oldest observable thing in the universe. It's all one story, from the smallest to the largest, from the newest photon to the oldest, all of it connected by the quantum field that fills every corner of existence. Let me tell you one more thing about what happens when light slows down, because it connects to a misconception that many people carry, and it reveals yet another layer of subtlety in this story. We said that light travels at 299,792,458 meters per second in a vacuum. In matter, it slows down. In air, it's a little slower. In water, it travels at about 75% of its vacuum speed. In glass, about 67%. In diamond, less than half. If the speed of light is supposed to be a fundamental constant, a feature of the geometry of space-time itself, how can a chunk of glass slow it down? Is a piece of glass breaking the laws of physics? The answer is subtle and beautiful, and once you understand it, it changes how you think about both light and matter. When a photon enters a piece of glass, it doesn't slow down in the way that a car slows down when it enters mud. Individual photons, between atoms, are still moving at the full vacuum speed of light. They haven't been slowed down at all. What's happening is much more interesting. As the photon's electromagnetic wave passes by an atom in the glass, the oscillating electric field shakes the atom's electrons back and forth. Those shaking electrons are themselves accelerating charges, and accelerating charges produce their own electromagnetic waves. So each atom in the glass, in response to the passing wave, emits a tiny wave of its own. These secondary waves overlap with the original wave. When you add them all together, the combined wave, the sum of the original and the trillions of secondary waves from the atoms, travels through the material at an effective speed that's lower than the vacuum speed of light. The slowing is a collective effect, a property of the combined wave, not of any individual photon. Between atoms, in the tiny gaps of vacuum inside the glass, each photon is still racing at the full speed of light. But the constant process of absorption and re-emission by atoms introduces tiny delays, and those delays accumulate over the thickness of the material, making the overall wave advance more slowly. When the light exits the glass and returns to vacuum, it immediately resumes full speed. Nothing about the light itself has changed. It wasn't tired or damaged or slowed in any permanent way. The glass merely created a complex dance of original and secondary waves that moved through the material at a reduced pace. This is why different materials slow light by different amounts. It depends on how densely their atoms are packed and how strongly their electrons respond to electromagnetic fields. Diamond, with its rigid, tightly packed carbon lattice, produces a strong response. Water, with its loosely arranged molecules, produces a weaker one. And it's why different colors of light are slowed by different amounts in the same material, an effect called dispersion. Blue light, with its higher frequency, shakes the electrons more vigorously than red light, producing stronger secondary waves that modify the speed more. This frequency-dependent slowing is why a glass prism separates white light into a rainbow. Each color travels at a slightly different effective speed inside the glass, and so each color bends by a slightly different amount. Newton's prism experiment, the one that started this whole story, works because of the interaction between photons and electrons in the glass, an interaction that's ultimately quantum mechanical. And researchers have pushed this to extraordinary extremes. In 1999, the physicist Lena Howe at Harvard slowed light to 61 kilometers per hour, slower than a bicycle, by sending it through a cloud of sodium atoms cooled to near absolute zero. 2 years later, she managed to stop light entirely for a brief moment, holding it frozen in the atomic cloud before releasing it to continue on its way. And in the other direction, researchers at the NEC Research Institute in 2000 sent a pulse of light through a cloud of cesium atoms and measured it arriving before it should have, as if it had traveled faster than light. This was actually an effect of the phase velocity of the combined wave exceeding the vacuum speed of light, and no actual information traveled faster than light, so Einstein's speed limit remained intact. But the result is a vivid illustration of just how strange light's behavior becomes when matter gets involved. All of this, the slowing, the stopping, the apparent speeding up, is a consequence of the interaction between the electromagnetic field and the quantum fields of matter. It's all quantum field theory, and none of it changes the fundamental fact that the vacuum speed of light is a fixed, invariant constant of spacetime. There is something almost poetic about the way this story has unfolded. For 300 years, the greatest minds in physics argued about whether light is a wave or a particle. They marshaled evidence, they designed experiments, they published papers and traded insults and staked their reputations. And in the end, both sides were right, and both sides were wrong. Light is a wave when you test for waves. Light is a particle when you test for particles. And what it actually is, deep down, beneath the measurements and the mathematics, is something that no human being has ever directly experienced. A quantized excitation of a field. We asked, wave or particle, for 3 centuries, and the answer was, the question doesn't apply. Light is something our everyday language has no word for. We can describe it mathematically, with terrifying precision. We can predict its behavior to 11 decimal places. But we cannot picture it. Not really. Not in the way we can picture a ball or a wave on the ocean. Because our brains evolved to survive on the African savanna, not to comprehend quantum fields. And the quantum world operates on principles that have no analog in the world of trees and lions and thrown stones. And maybe that's the most honest thing that can be said about light, after 2,500 years. We know how it behaves. We know the rules it follows. We can harness it and measure it and build technologies on it. But what it is, in the deepest sense of the word is, remains open. Not because we haven't tried, but because the question itself may not have an answer that human minds can hold. The fields are here. They've always been here. And they'll still be here when the last star goes dark and the universe grows cold, and all that remains is an endless, empty expanse of space-time, silent and still, with nothing left to vibrate and nothing left to see. But the fields will be there, waiting. And if some disturbance were to ripple through them, a tiny fluctuation, a quantum whisper, the vibration would race away at the speed of the universe, carrying energy and momentum through the void. Light, or something like it, would exist again. The field is patient. The field is always there. And as long as it exists, the possibility of light exists with it. So, after all of this, after 2,500 years of asking, what is light? Where do we stand? We know that light is an excitation of the electromagnetic field, a quantum field that fills all of space. We know that its excitations come in discrete packets called photons. We know that photons have no mass, and because they have no mass, they must travel at the invariant speed of space-time, the number we call the speed of light. We know that photons exhibit wave-like behavior when they travel and particle-like behavior when they interact with matter. We know that between interactions, a photon doesn't have a definite path or a definite state. It exists in a quantum superposition, taking all possible paths simultaneously, with the probabilities governed by a wave function. We know that when a photon is observed, when it interacts with something, the superposition collapses and the photon appears at a definite location, like a particle. We know that the electromagnetic field is just one of 17 quantum fields in the Standard Model, and that all matter and all forces can be understood as vibrations in these fields. And we know that despite all of this knowledge, despite the most precisely tested theory in history, there are still things we don't understand. We don't know why quantum mechanics works the way it does, why measurement collapses the wave function, or what, if anything, the wave function describes between measurements. We don't know how to reconcile quantum mechanics with gravity. We don't know whether space-time itself is quantized, made of tiny granular pieces at the Planck scale, or whether it's smooth all the way down. The 300-year pendulum between particle and wave swung back and forth for generations, and in the end, it didn't land on either side. It shattered. The question itself was revealed as too small, too limited by human intuition to capture what light actually is. Light isn't a wave. Light isn't a particle. Light is a quantum excitation of a field, something that has no analog in everyday experience, something that our language and our intuitions were never designed to describe. And yet, right now, as you're lying there, photons are arriving at your eyes from every luminous object in the room. Each one was born when an electron somewhere jiggled, disturbing the electromagnetic field, sending a ripple racing outward at the speed of the universe. Each one traveled as a probability wave, taking all possible paths, interfering with itself until it hit the atoms in your retina and collapsed into a definite, particle-like event, jiggling another electron, sending a signal down your optic nerve, creating, in the darkness of your skull, the experience you call seeing. You are made of the same quantum fields as the light. The electrons in your body and the photons hitting your eyes are all just different vibrations in different fields, fields that overlap and interact and couple together. When light enters your eye, what's really happening is that one field's vibration is transferring its energy to another field's vibration. It's all fields, all the way down. And the photons that are reaching you right now from the farthest visible star, photons that have been traveling for billions of years, for those photons themselves, no time passed at all. In the reference frame of a photon, if such a thing could be said to exist, the moment of emission and the moment of absorption are the same moment. Birth and death are simultaneous. The entire journey, billions of years and billions of light years, collapses to a single, timeless instant. Light exists in time and space for us, but for itself, it exists outside of time altogether. It's born and dies in the same breath, and everything in between, the stars, the galaxies, the planet you're lying on, the slow evolution of life, the 300 years of human argument about what light is. All of that is something that happened between the start and end of a journey that, from the traveler's perspective, never took place. That's light. The most familiar thing in the universe, and the strangest. The thing that lets you see everything else, but that you can never quite see clearly itself. A 300-year-old question that turned out to have an answer nobody expected. That the question was the wrong question all along. And if you're still awake, lying there in the dark, think about this. The room might look dark to you, but it isn't. Not really. The air around you is filled with electromagnetic radiation. Infrared from the warmth of your body, radio waves from distant stations, Wi-Fi signals carrying data through the walls, cosmic microwave background radiation left over from the Big Bang, a faint afterglow of the moment when the universe first became transparent, almost 14 billion years ago. You are bathed in light right now, light you cannot see. And every photon in that invisible ocean is a vibration in a field that has existed since the beginning of the universe and will exist long after the last star burns out. The field was here before you, it will be here after you, and for a brief, beautiful moment, a few of its vibrations are passing through you right now, on their way to somewhere else, carrying with them the story of everything that ever was.